ahead.
All right. Okay, well, thank you so much for this very impromptu presentation. So I know Dr. Pomorsky for many years ago. How many years, Chris? It's 2005, perhaps?
Something like that. Something
Yes.
like that.
So I just want to talk to you about some of the work I have been doing on fabrication and characterization of Josephson junctions. So I will start with a general introduction of the Josephson junction effect and the Josephson junction devices, and then we'll go through results from my undergraduate thesis. So from my PhD thesis, then a postdoctoral work at a lab that Dr. Pomorsky and I worked together many years ago. Then another postdoc I did at the Institute of Physics in Zurich, which is where I am right now. And finally, some of my recent work in America. Okay, so this is a small survey on Josephson junctions. And here you can see different types of tonal junctions and weak links. And I like to, if you like, to interrupt me and ask me questions as I speak.
Please make broader introduction, as this topic is new to my students. Thank you.
Yeah, let's see what can I tell you about this. From this, I went right into the topic. Okay, so what is a Josephson junction? This is a representation of it from the point of view of electronics, as you can see here. But it's basically, you can create the Josephson junction, or the phenomenon itself was suggested or discovered right after the microscopic theory of superconductivity, which is called the BCS theory. And please feel free to ask me any questions if you don't understand my accent, or if you want to if you don't understand some of the terminology I talk about, just let me know what and I will be happy to explain more. Also, I know you don't have any superconductivity background, right?
No, not much, because they're former students of computer science department.
Okay, computer science.
Yes,
but still, they attended the conference on superconducting technologies. Nevertheless, any type of background is highly welcome. Thanks.
Okay, so yeah, I would love to do that. And finally, my other question is, how much time do I have?
As much time as you wish.
Oh, really? Okay, because this is about 26 slides, but if we go slowly, this could be easily an hour. Okay, so you remember, or you know about the superconductivity effect, right? This is a something that happens in metals when you cool them down. Then the electrons somehow will correlate to one another, synchronized with the vibration of the lattice. So this was proposed by Bardeen, Cooper, and Schiffer in 1957, and the phenomenon itself was discovered at the beginning of the century, the 19th century, in 1909 by Kamerlingh Onnes, which was a Nobel Prize winner for that discovery in Holland. So he was the first scientist that had the ability to liquefy helium, and the temperature for liquid helium is 4 degrees at atmospheric pressure, so 4 degrees Kelvins. So that very low temperature gives him the ability to do experiments that nobody else in the world had been able to have before, because of the lack of this technology. So he took a highly purified piece of mercury, and then he cooled it down to basically the temperature of liquid helium. And right before the temperature of liquid helium is about 4.2 kelvins, at atmospheric pressure, right before that temperature, he noticed that the pressure, the resistance of the specimen dropped abruptly to zero. So that was quite unexpected. And then later he discovered that this was the sharpness of the transition between resistive and zero resistance was making think that this was something unique. So and that's where the name of superconductivity came about. So after many years happens after 2009, 1909, and then they come up with this microscopic theory, which is called the BCS theory. And then few years after that, there was a student at Cambridge. It was Brian Josephson, and he proposed, or he asked a theoretical question of what would happen with a pair of electrons. This is what's happening in the BCS theory. We have two electrons that will pair to one another, mediated by the phonon, which is the vibration of the lattice. So he asked himself, so if we have a chunk of superconducting material where all the electrons would be at the same state, quantum mechanical state, and then you separate another superconductor and you put them nearby, maybe separated by an insulating, a perfect insulator or other materials, what will happen to these the wave functions that represent those two states on the two different pieces of superconductors? So this is the idea of the Josephson junction over here. So you have a superconducting material on one side, separated by a junction that can be made by another material, which could be made of an insulator. This is the eye over here. I'm not sure if you can tell this, and then the other superconductor. And so basically, they discovered that there would be a tunneling effect between one side to the other, and then there would be an oscillating current, which is given by this equation here. This is the supercurrent that will go back and forth between the two sizes of the junction. And then this side here, this will be a phase difference between the wave function in one side and the wave function on the other side. And another thing that was discovered was that if you apply a voltage across the junction, then that phase difference would change with time, and it would be basically have this equation over here. So you'll have two equations that will describe fully the Josephson junction effect. So basically, when you create a junction that can be created in many different ways, like I was saying, a sandwich of two superconductors with an insulator, or you can make a sandwich with either a semiconductor, a normal metal, or another weaker superconductor. That is this S prime over here. You also create a Josephson junction. Also, there are many different geometries. You don't have to have a sandwich, but you can have an overlap between, for example, if you connect a normal metal and then you deposit across this normal metal, this bar over here. Let's see, I think my mouse froze. So if you connect this normal metal, somehow this superconductivity of this bar, this is a fully continuous bar that was deposited on top of this normal metal. This region that is in contact somehow will change. So you change the properties of this region. So there are several ways that you can create that. You can also create a constriction between a continuous film of two superconductors, and that will create also a junction. Or you can not only have a constriction in width, but also you can make it narrower. So if you can imagine how to construct this from the point of view of fabrication, that will also create a junction. And these are called point contact junctions over here. So you have a chunk of superconductors, and then you make another superconductor with a very narrow point, and then you smash one against the other. So that will also create a junction. This is called a block junction. So you have a superconductor of one material, and then you make a block of another one that's connected with all the imperfections that can exist among these two materials that you connect somehow. So that will also create a junction. So what was found that is remarkable is that the frequency, you see this is some kind of an AC current that would be established across the Josephson junction. So this phase difference between the wave functions of either side of the junction will oscillate at a natural frequency which is quite high. So this value here is called the characteristic voltage, and it is obtained by multiplying the critical current that is established across the junction, which is this basically this IC over here, and multiplied by the normal resistance that exists across the junction, which is in a circuit representation would be given by a current or a channel that the normal electrons will cross from one side of the junction to the next. So that the product between the critical current that flows in this channel, for example, and the normal current that goes across this channel will give you a voltage, which we call that the characteristic voltage, and that is related to the energy gap of the that is established in the superconductor. Have you heard of this terminology, the energy gap, before? I don't think I mentioned it before.
No, please explain.
Okay, so what separates superconductivity or the superconducting state from the normal state? So what is a normal state? What is a superconducting state? So normal state is the state where if we pass current through the system, there is resistance. Okay, so and this is temperature dependence. Okay, but then when we cool down the system, we have this phase transition in which the electrons no longer behave as fermions, like as we know they behave at high temperatures, but then they have this they relate to one another, and so they form a pair, and then this is a very particular pair from the point of view of quantum mechanics. So you have one electron, and then maybe Chris can explain this better than me about the Andrew reflection states, the bound states. But it's basically is the theory that he has used for many years. So you have the two electrons form a pair, and so they transition from being fermions as two different electrons to bosons as this pair, which they change, having a spin 1/2 into an integer spin. So the energy difference between when they are in the fermionic state to the bosonic state, that difference in energy, that's what we call the energy gap, and it's represented by this quantity delta. So every material has a different energy gap. So for example, in niobium, which is a material that I have worked in the past, it has an energy gap of about 3 milli-electron volts. So imagine that we can have create a junction where the product between this critical current and the normal resistance is right at this energy gap. So what we do with that information, so we get we will get a characteristic voltage of 3 millivolts. So this value of 3 millivolts, we put it into this equation. So we'll have an oscillating current back and forth, a super current back and forth in the junction, which will be about 3 times this value. So close to 1.5 terahertz. So this is quite difficult to obtain actually in real life, because most of these junctions have very low resistance. They can have quite high a critical current, but the normal resistance is mostly very low. Okay, so what I have described to this point are the classical Josephson junctions that were described and fabricated prior the discovery of high temperature superconductors. Now, high temperature superconductors are quite different. They are not the classical. They cannot be explained classically with the BCS theory, but we have to use different theories nowadays. And very recently, Chris, have you heard about a new theory for explaining high temperature superconductors?
It depends whether you really call it new. I mean, you say about Howard model or about, I mean, there are various, yeah?
Yes. No, there's it came about, I would say, less than 4 months ago. It's a new theory was explained that talks about in the D wave, it's really the electrons on the lobes of the D wave that they are correlated. That's how they explain the very short coherent length that is observed for high temperature superconductors. I think it's quite new. I was wondering if you have heard of that.
Well, I mean, it's, you know, the proclaim about existence of new theory is a very long one. There was many previous attempts to incorporate to describe extended Hubbard model. Then there was theory of repulsion as pairing mechanism. There was fluctuations of well, what was that? Fluctuations of, you know, there was even magnons. Some people even try to propose or exciton fluctuations. Anyway,
Exactly, the
there
exciton.
was,
That's the one that I'm talking about. The exciton fluctuation.
but saying so, it's rather proper to put link to the article, to the source of this information, because otherwise I'm afraid the information cited by you is not too much precise for us.
Yeah. No, I don't have that. I don't have
No,
this
it's
on this
somewhere
presentation.
somehow
But
later
it's
you can find out, right?
exactly, yes, yeah. So I don't have that information right now in this presentation, but it's something that I like to discuss with you in the future. So that's why I mention it right now. Anyhow, so we have classical BCS superconductors, which are mostly metals, and they were worked on prior the discovery of high temperature superconductors. So a high temperature superconductor is different. There is something that I didn't mention before, which is called the transition temperature. That is the temperature at which we go from a resistive fermionic state for the electrons to a zero resistance bosonic state of the electrons, if you want to call it that way, when the pairs are formed. So that temperature, which this transition occurs, that's called the critical temperature. Now, for most classical, most metals, the critical temperature is quite low. Mercury, the first metal that superconductivity was discovered in, this transition temperature is about 4.2 kelvins. But then we have another classical superconductor, which is niobium, for example, that is close to 10 kelvins. And so on. There are many alloys made with niobium that increase the temperature, the critical temperature, a little bit higher, but maybe 16 kelvins, no more than that. And that happens, that series of discovery happens from the beginning of the last century to maybe 1930 or something like that. And after that, nothing happened. But in 1986, some groups here in Switzerland were led to believe that the superconducting state could occur into some type of ceramics called perovskites. So they work on a system based on lanthanum, strontium, copper, and oxide, and then they were able to measure critical temperatures of the order of 40 Kelvin. So that was a big jump between what happened before 1986 to 1987, which they already had. They won the Nobel Prize for that discovery. And then after that, very quickly after that, a whole community of physicists all over the world started to experiment with different materials. And then I believe it was 1989, there's a combination of using yttrium. So they substituted lanthanum from yttrium, and then they added barium and then copper and oxide. And then they come up with the first superconductor that had a transition temperature above 77 kelvins. And that was very remarkable for the whole industry, because in the past we needed liquid helium, and as you know, it is very expensive to liquefy. It is not abundant, not very. This is a gas that is very a small percentage on the atmosphere. So it's expensive technology to need or for applications. It is a remarkable phenomenon. Having zero resistance, a cable with zero resistance is very important. We use it nowadays. We have many applications, but most of the time we require the use of liquid helium, which makes it a technology that not many people can use. So by the mid 80s or 90s, when many people were obtaining superconductors of different combinations with temperatures that were higher than the temperature of liquid nitrogen, then people were thinking, okay, we can change society using this technology. And why is that? Well, liquid nitrogen is much easier to obtain. We have about 78% of nitrogen in air, and liquefying this material, this gas is super easy, and it costs about maybe less than $1 for a liter. So that was a huge advantage that high temperature superconductors will have, but they are ceramics. So a ceramic material is much more difficult to operate. You need all the techniques. So that is what this table will show. So these are classical junctions with low temperature metallic junctions, but then these are what we can do, or the different geometries that the Josephson effect had been observed in ceramic superconductors. So this is called HTS, is high temperature superconductors. So basically you have somehow you create something called a grain boundary. So you use a substrate, and then you have a separation of between how you grow the superconductor on one side, because these are crystals. So and then the other. So if you have a different orientation, grain orientation on these two high temperature superconductors, or it could be even the same, but there is a clear separation between this superconductor on the left side and the one on the right. So that would be one type. You can see just some effect on this type of materials. Also, we have other things, like for example, this is called a grain boundary. So we have a substrate that somehow will have a ramp. So this is a junction that we see from the side. Okay, this will be from above. This will be from the side, and so we make a ramp like this. Also, we can grow a superconductor on top of a tunnel barrier. So that will also show a Josephson effect. Or we can grow in the same way as we did on this case here. We can make a sandwich, either some effect now for the new type of ceramic materials. And then finally, I want to remark this one, because this is super easy. So this you grow a high temperature superconductor on a substrate, and then you use a very powerful maybe the electrons from an STM tip, which is scanning tunnel microscope, or even from an electron beam microscope, you can irradiate just this region over here, and then somehow change the electronic properties. Basically, what was discovered is that you can remove the oxygen with the electrons. Very, very energetic electrons can remove the oxygen in the high temperature materials, because basically the oxygen is the most mobile element in the perovskite. So if you do that, you will weaken in a very narrow region the material. You will change it somehow. And so you basically create a junction, but in this case would be a bridge type of junctions. Any questions up to this point? Before I move to the next slide?
I have one question.
Yes.
What is the highest possible critical temperature for superconducting Josephson junction?
Yeah, this is a very good question. I believe that the highest temperature that had been recorded for ceramic materials was discovered by, was proposed or found by Andreas Schilling, and I worked with him at the Institute of Physics in Zurich, and it was on a mercury-based superconductor, and it's about 163 kelvins.
Wow! Oh.
So I can send you some of these. Let me see this. You can try to search for him, Andreas Schilling.
I have a question about the geometry of the junction.
Yes.
Because I don't think I fully understood how they are placed on the HTSJJ graph. So the A graph is from the side. B
This one?
is, yes, it's side view, B is diagonal view, and C is top view.
Yes, this one is top view for sure, and this one is side view, and this is also side view.
But on the different degrees. Okay. Thank
Exactly.
you.
So this one is the only one that
was-
is top view, and the rest are side views. And these are, these are three-dimensional.
Yes, thank
So
you.
this
I wanted
three-dimensional,
to make
yeah,
the exact shape of it clear.
yeah,
Thank
yeah.
you.
So, exactly. This is, wait, this could also be side view if you wish, but so the substrate is here, and then somehow there is a discontinuity on this part here. So when it grows, the crystals are grown differently in the interface between these two. So the substrate itself has to have something that would disrupt the crystallinic formation of the superconductor when it grows on top of the substrate. But yeah, I think this also could be side view or top view, because this is super simple. It's not much. But the point is that whatever there is a difference between this superconductor on the right and this one on the left.
So the central idea is very simple. You have, imagine you have a superconducting material. If you have a uniform superconducting material, if you send a current via this superconductor in such case, I mean, there's current flow without voltage drop. But when you make a constriction or narrowing of superconductor, when you modulate the uniformity of superconducting properties. So for example, you can do it by placement of superconductor isolated superconductor. So you interrupt superconducting properties very locally. Then you generate a Josephson effect. So two superconductors will interact between themselves in a kind of perturbative or non-perturbative way. And this is the essence of Josephson effect. So, but of course, there is almost infinite number, maybe infinite, quite big number of possibilities how you can tune the properties of superconductors. So then you have a wide class of devices or structures, right? And actually, it happens that the Josephson junction is a central circuit element in case of superconducting electronics. That's why it's this slide which it's given here is so well described, because it's quite essential to understand the essence. And then okay, the Dr. Gomez will give you more explicit examples how he plays with geometry and how he tunes the properties and what are the consequences for transport properties across the different type of Josephson junctions. But there's one very prominent feature, that current voltage characteristic in case of Josephson junction is highly nonlinear. That's very essential. That's not exactly the case of capacitor, resistor, inductor, but this is actually absolutely the case of Josephson effect. And then this nonlinearity is encoded in RCSJ model. So this is a resistor capacitor shunted Josephson junction. So so practically speaking, you have two fluids in a superconductor. One fluid is fluid of bosons that obey Bose-Einstein statistics. So it means that as many bosons can occupy a given geometric point as possible. So there's no limitation on density of bosons. And then there's a second liquid. This name is Fermi liquid. And then this second liquid component is component of unpaired electrons that obey Fermi-Dirac statistics. And in such case, two quantum states cannot occupy the same element. So this Fermi liquid is responsible for limited dissipation or friction that takes place in Josephson effect. That's how it is. So this is the central picture. This one that describes.
Exactly.
Okay, so sorry for a kind of local interruption.
Thank you, Chris. This is it kind of tunes me to the level that I need to go. But technologically, because you need to consider that besides a physicist, I'm really most interested in applications. So what can we do with these things? So technologically, we want to change the value of this critical current, which depends on the temperature. So this is if we cool down the junction to a lower and lower temperature, then we can allow for the system to pass current from one side to the other without dissipation. So that would be temperature dependent. So we can control this IC by temperature. But then Rn, it will be more a geometrical value, a geometrical quantity. So how can we create a different the junction by the different methods that I had described in order to tune this value? So these are the two different maybe sometimes even a little bit competitive or competing quantities that will give you this characteristic frequency. Now once you determine the characteristic frequency, then you have the oscillator that will have a natural frequency of oscillation at a different value. And as you can see here, it can be quite large with depending upon the level of characteristic voltage. And then most people in applications, you want to go to the highest possible oscillating frequency. So there is actually a gap technologically. We don't have a convenient system that will give you high oscillation at a higher frequency that can even be an antenna for these high frequencies, or it can be a transmitter for these high frequencies. So just some junctions can play the role for both if we can make use of this technology. So I think that's what is exciting about the use of just some junctions in this sense. And then just keep in mind this type of geometry, which will be a geometry that I will refer later in the talk. Okay. So during my PhD thesis, I studied two different systems. Basically, in the first system here is called an SNS just some junction array. So it's an array of just some junctions because Each one of these crosses, the black crosses here, is an island of a superconducting material. In this case, is niobium, and this piece of niobium was deposited on top of a film, a continuous film. In this case, was gold. So my system here was basically constituted on a gold island, sorry, a niobium island deposited on a superconducting film. And the other system that I studied on my PhD thesis, it was basically a film of niobium, which is represented by the clear path here. And it was deposited on top of an array, a square array of circular nickel dots. So there were you cannot see the dots here, but there were an array of nickel dots of the same diameter and separated a distance. So the diameter was 200 nanometers of each dot, and they were about the thickness was about 65 nanometers thick. And then they were distributed on a square array, and then from center to center, each one of those coins, if you want to call it, because they're actually quite thin. This from center to center, they were separated by 400 nanometers. So there was a gap of 200 nanometers from the edge of each one of the dots in all the directions. So somehow in my measurements, I determined that the electronic behavior of a classical Josephson junction array with this rather hybrid magnetic dot array, and then somebody deposit a film of niobium, they behave in a similar way. And I will show you that in a minute. So why is this a Josephson junction? Well, I explained this before. Let me just go back to the other plane. So if you can see here, somehow depositing a material like a superconducting material on a normal metal, there would be a Josephson effect. So in here, for example, this is a superconductor on this side, and then through the normal metal, there would be a tunneling effect of the Cooper pairs. So that's what we see here as well. So you can see this little gap. So the islands are not touching. So if the superconducting effect will be transmitted from one side of the sample to the next, it will have to go through somehow the underlying gold system, gold film. Okay, any questions about this one?
No, it makes sense.
It makes sense. Okay, so what I will show you later is that this system and these systems are they can thought in a way similar. Okay, so to do these measurements, so we have quite advanced capabilities for construction of cryostats, and this is very crucial because we need to be able to control the temperature very accurately. So we have to measure, do transport measurements, which is basically at a fixed temperature and a fixed magnetic field, external magnetic field. We need to do current voltage characteristics. And then we do this using the 4-probe method. So that's why we have this, for example, with through this this electrode, this side of the sample and this side of the sample, we send current, and then through these two electrons, we'll measure the voltage. Okay, so this is called the 4-probe method. And also there is to measure superconductivity, you have to cancel. There is because we use normal probes, you always have the superconducting effect when you measure resistance. You also are measuring the voltage drop onto the leads. So to cancel the leads, we can measure the voltage in one direction, and then on the other direction, then we add them up, which will cancel the voltage of the leads, but then we have twice the voltage drop of the superconductor, so we divide this by 2. So this is basically how we do the experiments, and we do this automatically. So we'll have to use some data acquisition program. On the other sample is the same. we have a central channel for sending current, and then we can use, we have many leads, so you can use this part, this lead and this lead to measure the voltage. And so this will be a longitudinal voltage, but we also have these leads here that we can measure the transfer voltage. So this is also interesting. I did some experiments with the measuring the whole voltage or the transfer voltage in the presence of magnetic, external magnetic field, perpendicular magnetic field. And then if you remember, I mentioned these are nickel dots. So they are magnetic. So I could somehow magnetize them or randomly assign a magnetization for each one of the dots. And that also shows very interesting results. Okay. So we need such a cryostat. So in this case, this is the one of the sleeve from the cryostat. This is a superconducting magnet that gives us 9 Tesla. And then we have, this is called a helium pot. There's a container for liquid helium. And then we transfer the temperature, and then we can modify it through these rods, and then make a separation between the main reservoir of liquid helium. In the outside, we have liquid nitrogen just to separate the temperature from the environment. And then closer to the sample, we have another cold point that can be variable. So there is a resistor here that can change the temperature of only this part. Actually, this is the cold figure. So this is the 4 kelvins. But then this will be a heater. There is a weak link here. It's made of brass. This is copper. So whenever we change the temperature of this region, that will change the temperature where the sample is. And then we have a couple of thermometers that we can, control this really well. So this type of system gave us a very stable controlling of the temperature in the order of millikelvins. And then this is a little bit of a representation of how the samples are measured. So the samples, we can apply also microwaves. So we have coaxial cables, which is these mini coaxial cables, into the sample, and then we can add, besides a DC current, we can have an AC component. So this AC component basically will add up to the DC voltage, and then we can do experiments based on frequency, and then change the characteristics, and I will show that later. So this is important to be able to add these AC signal to the system. Okay, questions on this slide?
I would say it's a bit overwhelming for somebody who see those things for the first time.
Okay.
It's so basically this slide, you are talking basically to a theoreticians that has only one semester of physics, maybe at most, in lab, and those guys mostly use computer for everything they do. Not always, but mostly.
It will be useful to describe some components in more details because it's a little bit hard to distinguish them when it's first time you see them.
Well, the whole deal is that you need to cool down the sample, and the cooling down of the sample is so inside this box that keeps the sample, there is a vacuum, so you have to pump out the air, and then you have only this cooling by this metallic part, or heating up by this metallic part. So the sample is supposed not to touch the walls of cylinder that shields the sample. So there are vacuum techniques involved, and there is of course mechanics, because sometimes you have to set the system properly. Well, you need to, at least old schools, you have to be able to transfer liquid nitrogen and liquid helium. So the whole system was quite demanding from engineering perspective, because there was elements of mechanical engineering and electrical engineering and vacuum engineering, and also material engineering. So So that's how it is. So
Yeah.
here the temperatures which are described on this slide, or the slide refers to certain range of temperatures, are not so much demanding because you don't go below 4 Kelvin.
Exactly.
And so this is a relatively easy area, but if you want to go for IBM quantum experience, you need to go to 10 millikelvin regime, and this is by farther more even more complicated than that one. But anyhow,
Exactly.
that's just first scheme of cryogenics that you can see.
Yeah, and this is basically because of the material that we chose to make our systems. So we use niobium. The transition temperature of niobium is about 10 kelvins, it's 9.2 kelvins. So with liquid helium, it was enough. If we use something like aluminum, which is most of the new technology for quantum computer transmons are based on, the Josephson junctions are made of a classical niobium, aluminum oxide, aluminum Josephson junctions. So you will need to go below 1.2 kelvins and even below that. So this is the temperatures that Chris was saying. So you need a dilution refrigerator. And so you have another level of complication. So we didn't have to go there because this is niobium. Okay, so that makes it easier. So and hopefully, when we move into high temperature superconductors, it will be even easier. But then that would require to get a quantum a state at such a high temperature, that would require a completely new technology. Okay, so and how do we control all this? Well, would you create it in-house a LabVIEW program? A LabVIEW is a program that you acquire from National Instruments that allows you to program in a language called the G language. And it basically, all the operations are based on connecting boxes that have cables connected among themselves. So this would be like the code, this part of this panel here, and then this will be the user interface. So the user will see this. So by adding several graphs and then adding some parameters here on this panel, then you would kind of enter the initial values for the logic, which will run in here. And so this big squares that you see here are basically for loops and while loops, and then there are information that is passed to boxes and then coming from inside and then out. So I'm not sure if you have seen this type of programming in the past, but this is a standard for data acquisition and also presentation. So this is
actually this is diminishing way of programming. This is so-called graphical programming. Guys, have you ever make a graphical programming by yourself?
No, I have never. You can use something like C to do it, or even
yeah, but you see, the point is the point is that education those days becomes very systematically less and less universal and more shallow. And this is almost not acceptable, but unfortunately I face this phenomena more and more often, that technical university only teaches theory without full access to equipment. Because usually in standard domain of teaching, theory supposed to be given at Department of Mathematics, let's say. But unfortunately, a lot of engineering departments, this is a paradox, becomes more and more decoupled from universal teaching, and there is a very systematic drop of number of hours of physics because it's not popular and demanding subject, and in even physics labs. So actually those guys, so to be very honest, many technical universities are only technical by name, because if those students doesn't have a real access to real equipment, they're not really engineers. I mean, well, you can call yourself to be engineer just by making programs, but then can always provocatively ask you, what's the difference between your skill and the skill of guys studying at Pure University? And actually you would discover there is no difference. So unfortunately, that's the effect of populism that we try to ease down, and we decouple students from real hardware into teaching theory. And here the lab view is just environment that you have a lot of measurement equipment and you want to synchronize the measurements.
Exactly.
So you cannot use 10 multimeters at the same time because you need synchronization. So you connect 10 multimeters so you activate them by means of LabVIEW. So in a such a way, you can have synchronized measurement that can be done during demanding experiments.
Yeah.
All more sophisticated measurement devices, they have ability to be programmed, or they have the ability to be externally controlled by a program, and this is LabVIEW.
Exactly.
So you put icons, and these icons represent a program. Those programs usually doesn't have a very sophisticated algorithmic structure. That's why this programming language usually is graphical. Nevertheless, that's the skill, and actually to shape, and also it is important that how to say, well, this okay, so you can only learn those things by being placed in a real lab.
You have to be in a lab.
Doing real task. You cannot simulate so easily cryogenic experiments by yourself. Also, I would say doing the cryogenic experiments, you will see the difference between this is what is expected, what comes out during the experiment. So, and also I would say Nobel Prize winners are mostly given for experimental physics, not for theoretical physics. And also natural science mainly bases on real experiments, not on theory, on real experiments. And this is very unfortunate that those days, even though that we have more and more technology developed, we do less and less experiments, which means that in a very real way, we become decoupled from real natural science. And so we only have imagination of the reality instead of knowledge of reality. And knowledge of reality cannot be fully obtained without experiment. All right.
Definitely. Thank you for this, Chris. This is the main point I want to transmit to your students. This is a lot of work, and this is nobody will give it to you. You know, this nobody will. You have to experience yourself. Any system that you like to study, and you want to learn more about. The only way that we have nowadays to interact with an electronic system will be by using a voltmeter and a current source. Okay, so you can do a measurement, maybe one measurement by hand, but you know, that will tell you very little. You have to do some real statistics. You have to do measurements under different conditions, and this is time consuming. So a human being cannot do that effectively. So you need to have to obtain the ability, the skill to interact with many different instruments at the same time. And then you could create a LabVIEW by yourself. You know, this is, you know, it was created a thing in C or Pascal or, you know, Fortran or any language that you might want to use. But also that will require a lot of work. There's a lot of synchronization. So I tried in the past when I was trying to do this, and I believe this was quite early when LabVIEW came out, and it is an expensive program. And then I was fortunate that the professors in the lab that I was in, they invested onto one of the versions. So you start learning the program. You start interfacing different instruments, and then writing your own interfaces, and see how you create a curve based on the measurements obtained from the instruments. And then you also have to make some assumptions, or you have to try to do measurements on things that you know, and then believe on the type of programs that you write. So if you write a program and you obtain some data of something that you know how it behaves, and it is within the certain error compatible to what you were expecting, then you feel that you are in a good track, and then you can change that system, maybe a resistor or whatever you put that is simple, into something much more complicated, like a Josephson junction, which is completely non-linear, and then you are not really sure how it will behave. So once you establish that level of confidence on your ability to measure and obtain good results, statistically valid on a new system, then you feel good that at least your data will be publishable, and people will believe that you didn't get any. I mean, it was not noise; it was something real. Okay, any questions? All right, so let's move on. So with a program like this,
here's what I found.
Oops, sorry, somebody's talking to me. This is the first thing that you obtain. So this is called the resistive transition. So resistance is on the vertical axis, and the temperature is on the horizontal axis of one of the samples with niobium on top of gold. So this is called the square sample. There are 300 crosses along the current direction, and 50 crosses parallel to that. So there are 300 in series, and then 50 columns of those crosses. And this is what it's called, this 300 by 50. And so as you go down in temperature, you get maybe a value which doesn't change with temperature. Basically, will be the resistance of the whole system, including the gold underneath. So gold is a normal metal, so below certain temperature, you just get a remnant resistance, doesn't change with temperature. But then all of a sudden, each one of the crosses start becoming superconducting, and this is right at 7.2 kelvins. This is the transition temperature of the niobium. So imagine you have gold that connects one end to the other, and then on top there are chunks of niobium crosses that they can be resistive, but then at some point they will become zero. The resistance will become zero. So this is the first sharp charge drop that we see here. Okay, so right at the temperature of when the niobium becomes superconducting. But then as we continue going down in temperature, there will be some tunneling between the arms of the crosses. So there will be Cooper pairs on each one of the islands, in each one of the crosses, but then they start tunneling. And then that's how you see this last transition into zero. So when we go below 3.7 kelvins, then we'll have zero resistance. This is how you will interpret this curve. Okay, and then this is the other system. This is the niobium film on top of the nickel square dots. So again, you have a region where the material is normal. The niobium film hasn't become fully superconducting, but the nickel somehow affects the niobium. So the resistance start lowering, not as sharply as on the first samples, which is more clean. You have gold that is not magnetic. So and then the transition occurs right at 9.2, but in this case it's about 7.9 when I can see that the transition occurs. Then it goes very sharply about 7.8 we almost zero. But then I'm not sure if you can notice in here, this not quite zero. It may be below 7.76, and I like you to see the accuracy of each one of these measurements. You know, I have a millikelvin control and stability for each one of these measurements, even from this system and that system. So, I mean, this was very remarkable. It occurs all the time. And I was able to zoom just to go back and do the measurements in here. So what you see here is what happened in here. So basically, we have a lowering of the resistance, but at some point, the resistance starts to increase. And I thought that was really unique. Also, I'd like you to see here the error bars. So this, you know, this each point is made with many measurements. So the error is calculated based on the discrepancy of each one of the measurements obtained at a fixed temperature. So I mean, this is the error is quite small compared to the value of the resistance. So we believe that this is true. And then, you know, again, past 7.766 kelvins is when we have zero resistance. So, you know, at this point, we had most error. There is most fluctuations. This is the size of this red error bar over here. But then on the other parts, you know, the error bars were negligible. Whatever we measured as the resistive point, which was calculated, basically, we send a fixed current, and then we measure the voltage in both directions. That's how we determine the resistance. So the ratio between the voltage and the fixed current. So there's more error on this region here than you have below, I mean, colder temperature, or even before that. So there is something going on in this region, which you know, I couldn't figure out. So how can we understand that? Let me see. What we believe happened is on this system. So in here, each one of the circles here represents a nickel dot. This picture is looked from above. Okay, so from above we see the substrate, which is this value, I mean, this kind of dark yellow color, and then you see the orange coins or circles. Sorry, the gray circles. This is the nickel, and then on top we have these two different color blue. So a darker blue, which will represent the niobium farther away from the nickel, and then a pale blue, which represents the niobium in closer to the nickel. Okay, so we think that this is the picture somewhere around this region. So in temperature around this region, you know, farther away from the nickel, the sample is fully superconducting. So there is this darker blue. So the film is because we are at this temperature is, you know, somewhere in between 7.8 kelvins and 7.7 kelvins. So that's way below the niobium transition. So we believe that the film everywhere, the niobium film everywhere, is superconducting. But right in between and where the nickel is, it's not superconducting, not fully superconducting. In fact, you know, there is a weaker superconductor. It's actually not superconducting because we're measuring a resistance. Okay, but maybe somewhere in between, farther away, the farthest away you can see from each one of these dots, there might be a pocket right there of fully superconductivity. Okay, so this is what we think is happening around this region. So you have two systems: this niobium system with nickel, and then we have an niobium system which are crosses on top of gold. So I think I made a movie where I will show you that if I put this system on top of this one, it basically the darker blue diamonds between the circles will be equivalent to the black crosses of niobium in the previous system. So let's see if this works. So that is the point then to say the two systems behave similarly if I do the experiments around this temperature. Okay, so if I'm not able to control the temperature accurate enough to be precisely enough to be on this region, then I will not be able to see the similarity between the Josephson effect of one system and the other. Any questions?
Okay, so just restate all the meaning of all colors for the structures described by you. So the brown means what?
So this will be the substrate. Yeah. So let me show you one of the first slides of, sorry, this one. So you see, the brown one will be these samples were grown on top of a silicon wafer. So the silicon wafer will be the substrate. Then in this case, this pale gray color is the niobium, and then this darker region is the where the nickels exist. Okay, so let me go back.
Yeah, because this scheme is not fully described. So black crosses means superconductor, right?
Yes. Hi.
Right.
Yeah. So the black crosses is niobium basically. Each black cross is niobium.
All right, and the blue color, what does it correspond to?
And that's also niobium in the other system. So yeah, so the black here is niobium, and the darker blue is also a fully superconducting niobium.
I can, in principle, I can try to attack such type of systems with the software which we developed. But anyway,
yeah. I mean, that's why I wanted to show to you that there is a great potential to use your expertise into developing, simulating the systems.
All right. I guess we have new people. We have Mikołaj among audience. He's from another university, from HGH University of Science and Technology, and there is Adam. That's a PhD student. Actually, Adam, it's good that you have arrived. All right. So okay, so just to make summary, because I just want to be very specific. So the brown color means the dark brown on the right. Dark balls means
these balls here. This is nickel,
which means superconductor, right?
No, nickel is just a magnetic material.
Okay. So dark balls.
Nickel is not superconducting.
All right. Okay. So I understand. I start to understand. So you place the network, two-dimensional network of Josephson junctions, and you place nickel is a ferromagnetic material.
It's a ferromagnetic material, yes.
So you place local sources of magnetic field. So somehow you tune the ground state of two-dimensional Josephson junction network, because there will be built-in magnetic field present due to presence of nickel balls. Okay, now I start to understand. And the blue one is what? The dark blue and light blue.
Exactly. So the dark is just a continuous film. So the whole blue color is, imagine there is a continuous film deposit on top of the array of nickel balls. These are actually like coins. Chris,
I mean, a big disadvantage of this picture is that there's no clear description what is what. So okay. So again, the dark blue is what?
It's niobium, but so imagine this.
But niobium playing role of superconductor, right?
Exactly. Niobium is superconducting material.
Okay.
Below 9.2 kelvins. So it's a metal.
So this is like decorated two-dimensional lattice, pretty much. So,
Exactly.
so two-dimensional superconducting matrix decorated by two-dimensional lattice of ferromagnetic dots represented by dark brown. Yeah,
Exactly.
that's that. And then on the top of that, you want to put Josephson effect as well. That's your
No,
not yet. I mean,
these are two different systems,
I see.
but they're completely two different systems. Let me go back to the to
No,
this
no,
slide here.
but there will be okay. This is different system. Yeah, I agree. This is completely
Exactly.
different system. All right.
Yeah, yeah.
So here you have two-dimensional network of Josephson junctions represented by black color, and
Exactly.
in between there is non-superconducting material that is yellow, right?
Mm-hmm.
And what type of material is that? Is that metallic? Is it semi?
It's a metallic. So yellow is gold. It's a film. It's a gold film, a thin gold film, continues from one side of the sample to the next, and on top of that we put the niobium, which is the black color. In the one system.
All right. So going to the next slide.
Yeah.
Then on the next slide, you have chain of ferromagnetic dots, and so the dark blue you said already this is a superconductor. The light blue, what's that?
Okay, so what you need to remember is that the film is continuous. The niobium film is continuous, and it has been placed on top. So the way to fabricating this, Chris, is that first on the wafer, the silicon wafer, we put the little coins, the ferromagnetic dots made of nickel. Okay,
Yeah.
so we put those first, and then on top we'll deposit the film. And then finally, once we put the film, as clean as we can make the interface between, or to deposit one on top of the other, then we'll do the lithography that will make the sample to be measured. So basically, so first you put the big square, it has the nickel inside there, then you put the film on top, okay, the niobium, and then you remove this part with photolithography. So, and then you make the electrodes. So to these ones you send the current, and then to this bottom one you measure voltage, longitudinal voltage from this side to that side, or you can also measure the transfer voltage across the sample this way. But then
yeah.
But, so the film, the niobium film, have been removed from everywhere except from where the path that makes the circuit, the circuit. But then this is continuously, and it doesn't show in there, but it's continuously on top of the nickel.
All right. Yeah. No, okay. Well, no. So somehow I understand this philosophy. Somehow, yeah. So, yeah. So there will be some, even by placement of such ferromagnetic dots, you might locally induce two-dimensional lattice of Josephson junctions. You might even induce because the ferromagnetic dots will always represent, in a sense, the origin of topological defect in superconducting order parameters. So even by proximity effect. So somehow this yellow-blue is simply weakened superconductivity, I presume.
Exactly.
There's no other way of, yeah. So definitely the system described by you could be grasped by Ginzburg-Landau formalism and by Bogoliubov-Dijen formalism. And my understanding is that all these materials are, this is pretty much their BCS superconductors. There are not no high TC.
No high TC.
So then the level of predictivity of phenomena and understanding of phenomena is much more higher than in case of high temperature superconductors, which is a good thing. And then you have resistance versus temperature. Yeah. So so this the very left is there's lat theory. Lat theory is abbreviation for lat theory is abbreviation of what? Larkin. Is it Larkin? Larkin, I think it is Larkin. Somebody else, Timken or something like that. That's no. I just try to get these features
The
of
lag theory. I hear you.
and be okay. Well, so the first sample is 300 times 50 V6.
Exactly.
Okay, okay. So then the current bias. All right. Okay. Well. That's the whole point is to model the diffusion of the behavior of quasi-particles.
Exactly.
That's in range of possibilities of this Boghoff-Dijon equations. I just imagine if Ginsburg-Randolph theory is able also to do it. Well, yeah, okay, I think it is, but in very limited capacity. Okay, so please move on, right? If there's no comments, unless there are comments from new guests, unless there are
just any questions so far before I move on.
I guess there are no questions, so please move on.
Okay, so what I want to emphasize here is that in order to have one system behave electronically like the other system, the temperature of this system here with niobium and nickel, it has to be placed one high location. It has to be over here. So I was very surprised to see that the resistance will go down to a minimum point, but then it will increase again. So this was really not expected. And when I looked at the data from my collaborators, they use other type of cryostats with the more inferior capacity for temperature controlling. So by not being able to control the temperature as accurate as we did, they would miss all this effect here. Why are you smiling, Chris?
No, not because of that. Not because of that. So sorry, I just get some accidental message. Go ahead.
Okay. So it's nothing to do with the talk.
No. I follow the talk. Don't worry. I have to parallel. I have few processes in parallel, so that's all. I'm sometimes getting it.
I will look at you again.
All right. All right. Go ahead.
So the point is that you have to control the temperature. You go in a region where there is this increase. So by placing yourself at this point, then you can have this image, that there is certain pockets of non-fully superconducting state. So by having a non-fully superconducting state in the regions nearby pockets that are fully superconducting, then you basically have the Josephson effect, where there are non-equilibrium quasi-particles or even copper pairs that go and tunnel through other regions that are also fully superconducting. And so, these are represented by these fully dark diamonds in between the circles. Okay, so these diamonds are like these squares, pockets of fully superconducting state niobium. This is just niobium, which I measure below the transition. That's why I had this very sharp transition temperature. So I got this region here that is where where there is the tunneling. But I also take a look at this graph over here and this graph. There is some similarity right there. There is a temperature below which there is zero resistance, the same as here, but there is a region here where there is actually a resistance in the system. Now, let me see. Can you see this? In this case, this is 200 milliohms. This is very low resistance over here, but in here we're talking about 3 ohms. Actually, sorry. This would be what Yeah, about the same order, 500 milliohms, no, 50 milliohms. But it's when I show you the measurements, you'll see that it's actually the resistance is quite high. All right. Any questions? I'll move on. Okay, so I place myself at one temperature. In this case is let me see, the fixed temperature is 3 kelvins. So if you look at the previous graph, 3 kelvins is somewhere around here where the system is fully superconducting. Okay, so it will be right here, right at the beginning of the transition. Sorry, at the beginning where the system has completely, becomes zero resistance. So I place myself at that fixed temperature. So take a look at the errors. This is even below a millikelvin of accuracy, and then this curve is the current voltage characteristic. So I'll send an increasing current between the two streams of the sample, and I measure the voltage using that technique that I was telling you about, where you switch the voltage polarity back and forth, and that remove the voltage drop on the leads. So you start sending current. There will be a region where there is no voltage drop. The voltage is zero, so that's fully superconducting, and that will give me a measurement of what is the critical current. So the critical current is the current that we can pass through the system without having any voltage drop, where the resistance is zero. Above the critical current, then there will be appears a voltage across the sample. Okay, so let me think about it. Okay, so this curve over here, if I take the dynamic resistance, so I take the derivative of this curve as a function of the current, then I get such a curve. So this would be the dVdi. This is the dynamic resistance basically of this curve. And then I can determine that at some point the resistance changes the greatest. Okay. So this is an important value here. So I would, from this curve, I can determine what is the critical current at a certain cutoff of voltage. So for this case, it will give me 140 microamps, and the current at which there is the maximum change in resistivity in this case is 540 microamps. Yeah, any questions about this graph? So this is the voltage current characteristic for the first system, the one that has niobium on top of gold. And then this is the same similar curve, but for the case of niobium on top of nickel squares, nickel dots. So this is a completely different system. So the film is actually continuous. So the critical current will be actually much higher. And here it's determined to be 413 microamps using this criteria. And then the maximum current or the current at a maximum change in resistance is about 800 microamps. So,
what's ST? What's ST? ST notation, ST.
This one over here.
Very top right. ST. Voltage is obvious.
Exactly. Oh, yeah. So in this case, this is the sample thermometer. So this curve here, it shows me what is
temperature.
the temperature of the sample.
Oh,
And
yeah.
now this sample has much more resistance. So as I do increase the current, the sample started dissipating. So my thermometer will start showing heating in the sample. So the sample thermometer, which is if I show you, it was over here. So I have a control thermometer is this one over here. This is what I use to control my heater. But then there is a thermometer which is closer to the sample, just farther away from the heater source. And so this one would tell me, basically it would tell me what is the temperature of the sample itself. So this thermometer is affected by the dissipation of the sample, whatever is happening in the sample. Okay, so that's why I wanted to show you in this graph. So there is a slight change, but it's less than 1 millikelvin. But if I zoom in, let me see if I can zoom in on this graph. If I zoom in on this graph, every point I'll show you the error values. So it's, they are quite small if I put this close to the scale. So it's just a fraction of a millikelvin. So then from this value here to that would be a millikelvin in change. So this is even a much smaller. Okay. So the two systems, IV characteristics, they are kind of similar. But since there are two different systems, one has a lower critical current than the other. Okay. So the next experiment is I try to add a radio frequency signal, so an oscillating signal on top of the DC. So I will repeat the previous measurement. In this previous measurement, there is no any AC signal added to the IV, but in here, these plateaus that are formed in voltage. This is what they call Shapiro steps. So there is a very precise values of voltage will appear a plateau that will correspond to the value of the frequency of the AC signal that is added to the system. So in this case, I added let's see, 50 millihertz of AC signal, and then using the equations, so we can see that we have these plateaus at a very precise values. And this is one of the beauties about the classical Josephson junction arrays made with niobium on top of gold gold film. So this is the remarkable correspondence between the experimental values with the prediction on the theory. And now I did the same thing for the niobium nickel sample, and I just didn't see that that change. Again, the ST here, this represents how the temperature changed in the system. So again, it's not quite, and there are many measurements of each point, so the error is just very small in there. And then I tried to do the experiment at a particular value. This is 7.8 kelvins, and if I show you the previous slide, so in here, 7.8 Kelvin is right here. So this is where the most steps data were taken for Shapiro steps. So around this region. So the only way that I could see on this, you see, there are not steps really appearing in the same fashion as I show here. Let me see, what is the frequency? Okay, the frequency is given by here. So I'm applying a signal which has is 2 gigahertz, so 2000 megahertz of frequency, and there is certain amplitude that is given by this 30 dB. So I take I don't have a way to measure exactly how much, what is the amplitude of the signal that I'm radiating into the system, but I have a way to attenuate this particular frequency amplitude that I am applying. Whatever the system absorbs is there's no way for me to measure that. But then I compare many measurements with different attenuations. So that's what I will show on the next slides. Any questions on here so far? So one system will show Shapiro steps very clearly. The other, I don't see anything.
Yes. So this is
about Shapiro steps.
Exactly.
Shapiro steps correspond to the frequency of signal. Then, in case of more complex wave function with multiple frequencies, would this create situation with multiple Shapiro steps?
Well, depends on the system. Yes, on the nickel system, yes, you have is very non-linear. I mean, it's not a classical Josephson junction system. So actually, it's a non-equilibrium system. It's a much more complicated physics and not very well understood physics. But what is remarkable is that as you apply the signal, you will see a response in the IV characteristics. So you can use then this system as a detector for signals. But on the naked eye, by a simple IV, the nickel and niobium system doesn't show anything. I mean, not like in the nickel gold system. In the nickel gold system, I put, whatever signal I put, if the array is perfect, I will get these very, very sharp plateaus. And then when I measure the voltage, well, they occur at a very precise values. So actually, if you make a perfect array system, you can use that as a way to as a standard, because these values correspond to, I'm not sure if you remember the one of the first equations that I show, just some equations. So these values depend upon this quantity. I didn't mention that before. This is called the quantum flux, which is the Planck constant divided by the charge of the Cooper pair, so 2e. So the inverse of this is this Josephson frequency. So it is related to the charge of the electron and Planck constant. So we have measured those values, these quantities at very high accuracy. So when we have this oscillating system that we can get a voltage value so precisely, then we can use that as a standard, because of the accuracy that we know these fundamental constants. And so this is just to give you an example of how beautiful we can change the voltage. And this is no trick on this measurement. But on the other
hello,
system,
Luis.
yeah, go ahead.
Hello. Yeah,
Yes.
this is Adam Hochlach. Hello, nice to meet you. I mean, because this is the very, I would say, intriguing phenomena, those plateau.
Yes.
You mentioned. I mean, what I see here, it's that the resistance, yes, but because this happening at the constant value of the voltage, yes, applied to the system, and if the current rises, that means that the resistance decreases, yes.
Yes.
I mean, yes, and I mean, what is the? I mean, what is my question is, do you all or do the physics understand how this phenomena happens? I mean, because I mean, well, the even more intriguing is that this I mean, as I see, this is the even very flat and near horizontal line. Yes, so that's mean that the resistance must decrease in some in very well like a controlled way. Do we understand this phenomenon? How it happens? I mean, what this how the resistance decreases in this case?
Yeah, so there is it's a synchronization. So what the way we understand this, so you have the superconducting phenomenon, which is
Yes.
all the electrons are they can move inside the superconductor, or in this case, it's just some junction,
Okay.
without dissipation.
Okay. So this is like a part of superconducting by basically the superconducting phenomena. Yes.
It's part of the superconducting phenomenon. So
Okay, thank you. So this is not something which is obviously observed just having the architecture of the system, or so this is the purely due to superconducting phenomena. Yes.
exactly,
This is
that's
okay.
precisely
Okay,
because
thank you.
it is superconductivity.
So this is not a matter of how you let's say how you build your system. Yes, this is not this is so we will observe this phenomena in other case also. Yes, this plateau.
Um, as long as it's superconducting, yes.
Okay, thank you.
In
I mean,
this case of
this
superconducting.
is but well I would say this is very well intriguing. I mean, this is the physical superconductivity. Yes. So
Exactly. Yes.
many thanks. Thank you very much. So
No problem. Thank you for your question, Adam.
yeah,
So,
thank you.
I cannot see that in the system, but what I can do is I can take the dynamic resistance. So as Adam is observing, in this plateau region, there is zero resistance. So if I take the dynamic resistance and I plot it, now, so I change the direction of the plot. So I take the current and the voltage, I put it like that. So the same curve. Now, instead of having the plateaus, horizontal, they would be spikes, vertical spikes. So I just switch the order, and then now I take the dynamic resistance and I plot that versus voltage. So and that would be the red dots here. So here we have my IV curve or the VI curve. Now is I switch the order, the axis, take my dynamic resistance. So right where these sharps occurs, the resistivity drops to zero. So again, it's like a reoccurrence of the superconducting state. That's for the classical Josephson array system. Now in the other one, so again I have a flat curve that I cannot see anything, but the dynamic resistance now shows me some dips similar to this one. So that's how I can see that something is going on the system with the nickel. So it's kind of like a trick. I just do I calculate the derivative as I'm doing the measurement, and then I can see I have so many different regions which I cannot see at the naked eye, but the calculation showed me that there is a region there with lower resistance. So I would take that this value is a step. So if I look at the calculations, now I use that I have a signal here of 2 gigahertz. So if I do the calculation by using the constant values, the charge of the electrons, constant Planck, and then using the fact that I have 2 gigahertz signal added, then the correspondence will be quite remarkable. So this will give me the first step, if you want to call it n equal 1, n equal 2, and then there is this correlation, and I was able to very accurately or within the statistics to show that there was a correspondence. So there was a number of junctions being added or formed in the other system, in the nickel and niobium system. So this is this N that occurs in here. So there are across the current path. Sometimes, if I do the calculation for one particular dip, I will get 91 junctions or 97 junctions, and this is at least the same order of magnitude of what I was expecting. I'm not saying that everything was perfect because the sample itself was not really perfect. I'm going to show you again another picture. So how many? I can count how many crosses are from here to here on the first system, but in here, I cannot even see the dots. But somehow there are these junctions being formed. So this last graph that I show you just is telling me that at least I had this number of junctions across this current path. So maybe you won't be convinced. I won't argue that this is not easy to see. But Chris, already how many hours I've been speaking to you guys? Maybe an hour, 2 hours?
I mean, you can speak as long as you like, under the condition that you are somehow understood, and at least certain level of questions shows
Exactly.
that there is some level of interest, and there is also some effect of novelty. So please continue.
Okay, so yeah, so I wanted to just emphasize that there is some correspondence. The data, you have to really be clear on what is the image of the system to really try to understand the results from the data. So the basic picture is that if you place yourself at that particular temperature, and again, I will show you here, it is 7.8 kelvins. If you place yourself there, then you can imagine that the system with nickel is behaving as the system with gold. All right, so then some of the results will be similar.
Okay, Luis, can I ask you? I mean, because the picture number 2, I mean, this is the one to right, yes, with the blue dots.
This one? This one?
No, the right. I mean, you mentioned that we observe here, right? I mean, because there are, let's say, a certain number of junctions connected in series, right?
Exactly.
Okay, so each those, let's say, the drop of the okay, I understand. So we can observe, let's say, each junction behave in different voltage, right? I mean, well, maybe not behave, but they somehow shows their physical, let's say, physical phenomena. Yes, so this is like a serious connection of certain number of. I mean, this is like number of 6, right? Six
Exactly.
junction,
yes.
6 junction connected in series. Okay, thank you. So and
Yeah.
then to this series, the voltage is applied, right? I mean, some kind of well, from the generator, right, or something. This is and then the current voltage characteristics is derived, right? This is how it's
exactly.
measured. Okay, thank you. Yeah. Okay,
yeah,
so
Adam, you go ahead.
No. I'm just because I was focusing on the. I mean, because we may ask also if the, let's say, the frequency has any well, let's say, has any influence on this well, the characteristic, right? Because this is 2 gigahertz, right? So
Exactly. 2
maybe
gigahertz.
2 gigahertz. Yes. So this is very high frequency. Yes. And the attenuation is 30 decibel, right? So this is
exactly.
so this is, I think, this kind of electronical value or level of signal, yes.
Exactly.
So because do you somehow try to change the frequency and see if the characteristics has any let's say change. I mean,
Yes.
let's say yeah, because the question might be right now if that frequency has any influence on the phenomena. Yes,
It does. It does have.
Does?
So as you increase the frequency,
I mean, well, let's say, but because 2 gigahertz is, let's say, sufficiently high. Yes, we can also decrease the frequency. Yes, and
exactly.
see if we say if let's say if the superconducting behaved let's say similarly in different frequency let's say range. Yes,
Yes.
I mean this is okay. So thank you.
Yeah.
I mean, well,
Yeah. No,
okay.
this is awesome, Adam. Thank you for all these questions. So what you need to imagine, Adam, is that each one of these junctions, just some junctions, they have a characteristic frequency. So this is the important point. And how do we obtain that? You were a little bit didn't come earlier, but let me just go back. This characteristic frequency is given by this value here. The critical current and the normal resistance. These are dynamic values. So these two values depend on the temperature and also the geometry, how these junctions are. So that will give you a precise value of these, how the current oscillates in a junction. So it's given by, it's related to this characteristic voltage, which is the product of these two values, is related to the quantum flux, which is a direct consequence on the Planck constant and the charge of the Cooper pair. So that will give you the Josephson characteristic frequency, oscillating frequency, and that is a value that depends on each system that you study. So you make a junction, and you need to measure these two values to know how high that frequency is or low. Now this is like an antenna. So if you go below that value, too far away from this optimum characteristic frequency, you might not get enough coupling. Okay, and if you go above, then you enter other factors, all nonlinear factors that will not make the coherence of all the oscillations between every junction. So you have to be kind of right there where the characteristic frequency is. Otherwise, you will not get a good signal. Okay.
Okay, and because this is very, let's say, interesting, because this is like a very let's say the feature of let's say like a microelectronics. Yes, and it has a very, would say, like a useful and
completely apply. Yeah.
yes,
This is
yes,
one of the most
applicable features. Yes, this
it's
is
one of the most applicable systems in superconductivity. You can do a lot of things with that Josephson junction. Yeah, and then maybe towards the end we'll talk about how to use that as a qubit. I'm not sure if you guys know about that.
Okay, last question. The picture of the right, yes, HTSS Josephson junction. This is the, let's say, okay, this is the, let's say, like an architecture of the Josephson junction, right?
Yes, exactly.
Okay, so because there can be, let's say, different setup of this junction
different setups,
at the semiconductor, let's say, wafer or something.
Yes. So actually, these are fully superconducting materials.
Yes, yes.
These are made with high temperature superconductors, and these are with low temperature superconductors.
So let's say it can be, let's say applicable for the let's say some microelectronics, let's say even devices for some let's say maybe voltage, current, or some signal shaping or something. Yes, this is something. This is something which has very, very nice physical features. Yes, okay, thank you.
Yeah, it's super applicable. Yeah.
Thank you very much. Thank you.
Okay, so let me go back to this curve that we were discussing. So I hope that to this point I had convinced you that there is the two systems cannot behave similarly. We'll have dips that will represent the location of this of these plateaus that are very, you can see directly on the classical, niobium over gold system. And on the other one, we don't see those dips and naked eye, but when we take the dynamic resistance and we reshape the graph, then we can find this location, and then doing some calculations with the equations that I showed earlier, then you can measure a number of junctions that exist. Okay. And then the next thing that we do is that this is a much more difficult curve for me to explain, but in here we change the value. So Alan, you asked me if I had changed the amplitude, for example. So basically this is the curve that you obtain by changing the amplitude of the curve. So this is the current, the amplitude of the oscillating frequency, sorry, the oscillating current that is overimposed to the DC current. So we put this RF because it's a radio frequency. So from the megahertz to the gigahertz, that's still the radio frequency frequency. And so as we change this amplitude, then we'll have that the width or the length of those steps would change. So this curve will show me how we call this the zero step, this delta I0 is called the zero step, and this is how the maximum changes with amplitude. And so I do many measurements similar to this one. Okay, and then the zero step will be the first one, that occurs here. This is the first step, the second step, the third step, and so on. So and then as I change the amplitude of the signal, in this case is 1.4 milliamps, and I can change that to any value by changing this amplitude, then this in this case the height would change, so it will be bigger or smaller, and then I plot that on this graph. So the red one will be the zero step, which is basically the critical current, how it changes with apply RF signal, and then this is how the first step. So the first step is again this one. So this one again will oscillate.
Okay, I mean, because as I think, I mean, because this is the still, I mean, this is kind of, let's say, the phenomena is due to this Josephson junction characteristics. Yes, exactly. I mean, yes, exactly. The Josephson junction characteristic governs this steps basically, and then this, because this is the current and okay, arbitrary, yes, okay, and this is and the frequency is much lower. Okay, this is let's say like a 50
exactly.
megahertz. So, it's well, okay.
Yeah, so I changed. This is in this case is much lower. The frequency is much lower. Okay. Because that product, the critical current multiplied by the resistance its value is much lower.
Okay.
So I don't have the number here, but
well, as I see, because let's say, for instance, I mean, in any other, let's say, like microelectronics, or let's say even conventional, like the junction, let's say what we see, I mean, for instance, in a classical microelectronics, yes, that frequency has let's say that the capacitance has plays the importance rules, yes.
Exactly.
But let's say if we don't see any, let's say, sufficiently changes in this characteristics, this means that the key rules plays the superconductivity phenomena in this case, yes.
Yeah.
So what I have understood, yes.
Yes.
Okay. So
yes.
Okay. Thank you.
So you have an oscillating system that has a characteristic frequency. If you play with the values around the characteristic frequency, then you get the maximum response. If you go away from that characteristic frequency, then you don't see much changes, even though you change many things in the system. So as a way to 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 be excited about the measurement, you place yourself right where that characteristic frequency for the system is. You make some changes, and then you can in that way you can characterize the system. So this is the characteristic of many measurements done at a different values of amplitude, and then this is the same one for here. But again, this one doesn't change. No, let me think. Exactly. So actually this red curve is not the same as this one. This red curve represents the temperature of the sample thermometer. Maybe I should have changed the colors so not to make it confused. But so this is just the value of the how the critical current, the zero step changes with the applied RF signal. So again, here is just a fixed frequency, but the amplitude changes, during the measurement. But as we increase the attenuation or reduce the attenuation, then we're hitting the sample. That's why for the first time here for small values of the applied current, there is almost no change in sample temperature. But as we try to increase that value, then the temperature will heat up. So this the measurements over here, which basically nothing is happening, but we cannot be certain that we are at the same state of the system because the temperature changes. But how much does it change? It's really, I started my measurements about 7.8 kelvins, and then this from here to there, there's just one what is that, 10 millikelvins change. No, sorry, not 10 millikelvins. That's it's even less. So this is half a millikelvin. This is 1 millikelvin. So this is really, I can determine that the sample is being heated, but it's not really that much if you think about how small the temperature change is. But this is just to give you an idea of how accurate you have to do the measurements. Some other systems, if you look at the specs, they don't give you that much control. But you guys are theoretical, or theoreticians, so you might never really appreciate the effort that was put into doing these measurements.
Yeah, okay. I'm let's say I'm impressed with for the resolution of the temperature measurement. Yes, because we are at the level of 7 Kelvin. Yes, so
yes.
7 kelvins above the the zero, and the resolution is you've got a very, very nice sophisticated measurement setup, because this is let's say 100 micro kelvins. Yes, this is the okay. So yes, so this is, let's say, I see that if this is visible only at this certain, let's say, the certain values. Yes.
Yeah. So that's why my colleagues really, they could never see this. For them, this was a non-existent, because for one point to the next, they have a let me see, some of the commercial systems, I would say 100 millikelvin variation. So you have to go 3 orders below that to see it. All right, so I'm sorry guys, maybe I'm being too detailed on that. I'm not going to tell you, this is more consequences of that. I just want to move on to another system. This was basically my PhD thesis. And this last measurement, this is with magnetic field. So as you apply a perpendicular magnetic field to the sample, then if you measure the resistance, how the resistance goes with the applied magnetic field, it also has these dips. Okay, so basically, if you look at the system here, you will have having four Josephson junctions arranged in this fashion. This creates what's called a squid. So there is a correspondence between the area that is forming here between this superconducting loop, if you wish, and the magnetic field. And so this is what this measurement shows, that anytime that there is a correspondence between the applied magnetic field and the flux of related to the quantum flux that goes around the plaquette, that's that square, then we'll have a minimum. So I was able to see that, of course, in the classical Josephson junction arrays, but also in the system with nickel, there was a dip, and I did some calculations. I'm not sure if I showed them there. Let's see. And the correlation was remarkable between the size, the 400, on this system, this particular plaquette, this is about 200 nanometers by 200 nanometers. So this size in the applied magnetic field on the other curve, it would show me, it would do the calculation that I would need to apply about 116 gauss to produce one quantum flux, and that shows.
So, okay, basically, this is the characteristic of the, let's say, sensitivity on the let's say, external magnetic current change, right?
Exactly. How the external magnetic field changes the characteristics of the sample. How.
Okay.
Corresponds.
Okay, thank you.
All right. So that was basically my PhD thesis. Studying those two things. And then, thank you. After that, I moved. After graduating, I secured a position at Professor Maeda's lab, and that's where I met Professor Pomorsky. Not Chris, am I pronouncing your last name right? It's been so many years.
Correct.
I think I still say it wrong.
Correct.
So when I arrived there, Chris was doing his master thesis, and he was experimentalist. So we collaborated in some measurements. So although it was not quite, but I wanted to put his picture in here to show you the people that we work with. Later, Chris went to work with Fujimaki, and did you finish? No, you did one year, right?
9 months. Nine
months with Fujimaki Sensei, and then you went to go to Krakow to graduate to get your PhD, right?
No, Fujimaki was after the PhD.
Oh,
Yeah.
You did a postdoc with Fujimaki.
Was my first postdoc, actually. Yeah.
Okay, great. Yes, I remember that. Somehow, I visited you when you were still doing your PhD at Krakow.
That's correct. And you gave similar, not the same, but you also gave a presentations. Yes, correct.
Yes. So anyhow, we coincide with in Japan in the year 2005, and then we were involved with Professor Fujimaki in doing terahertz electronics. So he's an expert on the single flux quantum technology, and by using a certain type of Josephson junctions that they have a characteristic frequency, a very high characteristic frequency in the order of terahertz, and so we can create systems that oscillate at that frequency, and then it's again I will show you this graph or this equation again, that the characteristic frequency, the characteristic voltage that we see in the junction, which is the product of the critical current by the normal resistance, if this is high enough, then you can be at almost 500 gigahertz, or if you have 1 millivolt or higher. Let me turn on the light here. It's getting quite dark. So maybe it's a little bit better. So if we change these values, then we have oscillators that operates at a higher and higher temperatures, but there is a limit. So we cannot exceed this energy gap. You know, if we go above this value, then basically we destroy the Cooper pair. So we have to go below, we have to stay below, and the energy gap is a quantity, is the energy separation that you go from the Fermi state to the bosonic state, and that is material dependent. So every material has a different value. So let me go back. Any questions to this point?
No, please go ahead.
I guess not, unless you go back to one of the plots.
This one here?
No, before.
Yeah, let me see. We got this
Oh,
one.
this no, that one on the left. Comparison of two. No, next one. Next slide. No, there was already. Come on.
This one?
Yeah, the left one. Yes. N equal 0 and equal 1. There is a correspondence to Shapiro steps, right?
Exactly. So these are the Shapiro steps. So this actually comes from this slide. So you see, so this first tip is the 0 Shapiro steps. This one is the 1 Shapiro step. This is the 2. This is the 3. You know, they occur. So the first one is related to the critical current, and then so on. But on the system with nickel, you know, I was unable to see nothing else but how the applied signal, the RF signal, the oscillating current, how that changes the critical current. So this only has the N equals 0, but then this one has the, I showed both the N equals 0 and the N equals 1. And then,
I don't understand. On the OX axis, you have ERF in arbitrary units. Is it intensity of microwaves?
Exactly. That's the amplitude of the microwave applied.
From coaxial antenna placed in proximity to the sample. Yes, but
exactly.
Why this intensity of Shapiro steps drops with bigger intensity of microwaves? That's quite strange, don't you think so?
Yeah. Yeah, when you solve the
Yes.
equation, let me see, there are some questions here.
No, not much questions, just comments. Yeah, okay.
Okay, got you. Yeah, when you solve the equations, when you write down the equations, the solution for the equations of the Josephson equations will be some kind of a Bessel function.
I know that. This is standard
so that's basically what it is.
Standard Timken. No, but this is a little bit against intuition. Anyhow, okay. Okay, anyhow.
Yeah, exactly. So mathematically, when you try to solve the equation, the only solution are some type of modified Bessel equations, and then this, if you remember how they look like, they are like this. So the correspondence between the experiment and the theory is quite remarkable on these classical systems. So, on the other one, yeah, I mean, I can see, there is this drop here, like I didn't see it bouncing again, but definitely, if I apply an RF signal, that just, consumes the critical current on this system. So that this dropping here will be similar to the first drop on this Bessel function. Yeah, I think I made a mistake here by the using of the colors. I'm going to change that for the presentation that I give later, Chris. This you caught me quite you caught me to do this presentation quite quickly. So this is a little bit
that's the way to activate people. If you give people too much time, they don't usually activate so easily.
So anyhow, let's go on. And so we go back to this. So there is a lot of application, guys, on these systems. And basically, it's a hot topic of research, is this terahertz electronics. So once I finished my PhD, I had the notion that by using these magnetic dots, the nickel in this case, I was changing the whole dynamics of the system. So in the past, all the classical Josephson junctions that I show you, we're just separating somehow the two superconducting islands, either by an interface with the, insulating non-magnetic or even, but there's nothing about magnetism. Okay, maybe there is some magnetism now, but when I arrived to Midas Sensei's lab, I told him, why don't we use some kind of magnetism to create a junction? And then he, agreed with my approach. So the first thing that I did was just to recreate a cryostat similar to the one I did for my doctorate. So this is a Midas Sensei's lab. Chris knows it really well. We were, compared to other labs in the US or in other places, we were very basic there, but with a lot of work, we created something. So in this case, the materials that I studied at this time were high temperature superconductors. So nothing like niobium. It was actually YBCO, or no, in this case it was lanthanum strontium copper oxide. The transition temperature for those materials is about 30 to 40 kelvins, depending upon the doping state of the superconductor. And so I needed a different type of cryostat. And now it would be a nitrogen cryostat. The nitrogen temperature is at atmospheric pressure is 77 kelvins. So I needed to have a way to be able to change that value. And so this particular cryostat, I could change the temperature between liquid nitrogen, liquid helium, and above liquid nitrogen. So from 4 kelvins to 100 kelvins. And then I had a small magnet. It only produced 350 Gauss, unfortunately. We created that ourselves. And then I have a microwave source of up to 20 gigahertz. So I could go from 2 gigahertz to 20 gigahertz. So there's not a lot of microwave that I could create that way. And then basically this coaxial cable and then this ended antenna, that shine the microwave onto the sample, and the samples can be placed in here. And then we have, on each side, we have about 5 electrodes. So we can measure a total of 20, have 20 different leads that could go to a complex circuit. So this was one of the first samples that we made. Basically, it is a high temperature superconducting film. And well, you don't see it here very well, but I would make bridges of different width. So the number here will be the width of the bridge in nanometers. So this is 400 nanometers.
I have one question. What the high temperature means in this context? 10 kelvins?
No, in this, because the system was lanthanum based, is 40 kelvins, around 40 kelvins.
Oh, 40.
Yeah, so for
impressive.
lanthanum strontium copper oxide, and at the optimum doping of strontium in the system, the maximum TC is about 40 kelvins.
Yes, very impressive. Thank you for clarification.
Yes, you're welcome. So just a film that one of the students will make using a pole laser deposition. So we time the thickness of the film by the time that we have the pulse going in the experiment. And those also, we have different targets that have different doping, so we can make samples of different electronic properties. So we create a film. I believe the substrate is also a lanthanum-based crystal. We create the film, and then using e-beam lithography, we will remove some of the parts of the film. So we create the bridges that you don't see really well here, but this will be 400 nanometers wide at whatever thickness of the film has, 300, this will be 200 and 100. And in between, there will be a bridge that we use as a control sample. Okay, so to create the junctions, we will deposit onto those bridges, we will deposit another material of, in this case, will be a magnetic material. So for this particular example I'm showing you, we use iron. So these bridges will have a particular iron strip that of this width. Sorry, I missed my pointer. And so this will have no iron, as well as this one. And then this one will have an iron island of this width, 300 nanometers, and so on. So this is the type of measurements that we obtain. If we do the resistance versus temperature characteristics for the sample that has no iron, so either this one over here or this one over here, we'll get the, a transition similar to the ones that I showed you earlier, but in this case, the drop of resistance will occur about 30 kelvins. But then if we measure the same one, in this case, I'm showing you for this sample that has the 300 nanometer width iron strip, then what we see is that the resistivity before the transition is much higher. And also when it started to drop, it's about the same temperature, but it becomes fully superconducting at much lower temperature. So somehow adding the iron to that bridge made of lanthanum, this is the dope in this case is the optimally doped strontium sample. So there is 0.15 atoms of strontium or components of strontium in the sample. By adding the iron, we will increase that resistance that is observed before the transition. And then when it's superconducting, fully superconducting, of course we have zero resistance. Okay, then any questions? So if I magnify what's happening here, I just choose to show you the values between 14 kelvins and 28 kelvins. So again, the curve with black is the transition for the bridge that doesn't have any iron, and the other one is how much lower we have to go in temperature in order to obtain the fully superconducting state. And then after we choose a particular value of temperature, in this case is right here at 15 Kelvin. So this curve is the current voltage characteristic at 15 kelvins, which is somewhere around here. So it's fully superconducting. The sample that has either no iron or iron. So it's both they are fully superconducting, but the IV characteristic is completely different. So the one that has the iron, the critical current is much less, and and also the resistance is much less if you well, actually I will have to get the dynamic voltage of this region here to find the resistance. But anyhow, here you can see that definitely the critical current is much less than on the other system. So let me see what values I get here. I will have a fully superconducting state of about 300 microamps versus 1 And here I measure 20 microamps. So from 300 to 20, that's how much the critical current had been reduced from one system to the next. Questions?
Well, basically, we get, let's say, like kind of a family of the characteristic, which is dependent on the temperature. Basically, yes, what I see here.
Exactly. Yes.
So like
yeah,
a family of the because the let's say if the characteristic change its shape due to temperature, yes, we got like a. But my question was, do you have, let's say, I mean an idea of the, let's say, the practical application of this kind?
well, what we see here is that if I take the value of, for the red one, if I take the value of the characteristic current,
Yes.
the critical current, 20 microamps, and then how I measure the normal resistance in here is 1 kilo ohms. If I multiply those two things, I will get a characteristic voltage of 20 millivolts.
Yes.
So that would be 20 millivolts. If I put that into the other equation, that will correspond to about 1 terahertz. So
Yeah,
if this,
well, I mean, well, what I was thinking, like, let's say, like a month ago, or when I was starting. So this is kind of, let's say, because you say the terahertz, yes. So this is for the very sophisticated, like a radio frequency application, for instance, yes.
exactly.
Where because you don't have a noises here. I mean, let's say because with the classical electronics, the noises is due to, let's say, the temperature recombination of something, on electrons or
Exactly, yes.
yes. So and here you've got a clear, let's say, clear shape of some kind of let's say the junction, yes, or clear shape of some let's say phenomena which is at the, so for instance, like a radio, let's say radio setup, or for the very high frequency, because what I know is that the, let's say, in a gigahertz, let's say the difficulties is it's, let's say, due to noises, basically, yes. And here
Yes.
we don't have this. Okay, thank you.
Yeah. Well, we might have the noises. There is a controversy about what is the origin of this such a high resistance in this system. So there is something I didn't mention so far, is that what we believe that inside of these systems there is something called a vortex of current, because this is I don't want to go into the details of all of the different descriptions of this type of superconductors. They're called type 2 superconductors. So they are highly, the lines of magnetic field can go very across this system everywhere. So there will be some weird loops of current going around each line of magnetic field. So this is called a vortex. And then if you try to move push current through this system, then those vortices will move. So some people talk about that type of things. I'm not completely convinced that this is the case, but what I can see experimentally is that I have a high resistance value. If I measure the resistivity at this point of the curve, and then if I multiply this by the current, that gives me about 0 voltage. Then I had these two numbers, I multiply them, I get 20 millivolts. And then I use the other equation, and then this actually will be 10 terahertz. That would be the characteristic oscillating frequency of this system, if this is a Josephson junction system. So that is the part where I had not completed this research to really prove that this is the case. So it is not easy to get a 10 terahertz source. I'm not sure if you realize that. I mean, maybe we have electronics or possibilities to create 300 gigahertz, but 1,000 gigahertz is just not possible. I mean, it is possible, but you need a laser or something like that, which is not something that I never had access to such a high frequency source. Okay, so I hope that you can see what the difficulty I had to prove that this system is really the Josephson junction system that I claim it is. but yeah, thanks, Adam. This is, you know, if this is, if I can really, if I am creating a system that oscillates at such a high frequency, then it would be remarkable the type of electrons that we can create with them.
Well, I mean, let's say that well, as far as I remember from my, let's say, not even university, but from my experience, I mean, well, let's say the commercial, let's say electronics deal with the frequency up to, let's say, 50 gigahertz. Yes, I mean the physics. Yes, yeah, it's too low. Yeah, but it's too. But well, I understand the physics has the frequency much higher. Okay.
Yes.
Okay. Thank you.
Okay.
Yes.
No,
Well, let's say, I mean, the let's say the radio link at the telecommunication. Let's say the higher frequency is, like, I think it's 30 gigahertz. Yes.
yeah.
And it's it and this what I remember, this is due to let's say basically the physical phenomena of the sensor and the transmitter. Yes, the antenna can, we cannot go even higher because, let's say, in conventional semiconductor, we don't have, let's say, enough. Well, I mean, there are certain of reasons why the frequency cannot be even higher, but let's say that this is the size of the basically of the semiconductor devices. Yes, because the wavelength at the 30 gigahertz is very small, and we go very narrow. Let's say the size of the semiconductor devices. Yes, basically. But
Exactly.
here, yes,
Yeah. I mean, if we want to operate at these high frequencies, then the sample, I mean, the detector, the antenna, will have to be much smaller than this, or at least the same size of the wavelength of the signal. So
yes, exactly.
yeah,
Yes.
so if you make anything bigger or smaller than that, you won't be able to couple the signal. And not only that, there is also the impedance mismatch. So you have the signal is created and maybe transmitted through air, and there is there is an impedance to send the signal through air. So the impedance of my transmitter will have to be comparable. I think it's either 75
Yes, I mean,
or
this is the matching of the let's say the impedance between antenna and the transmitter. Yes.
exactly.
Yes, I understand. This is, I mean, so this is the technical telecommunication, let's say, the feature. Yes, that you need to
Yes.
be, you need to be, because otherwise you get the dissipation of the energy in any, let's say, direction, not into antenna. Yes, if antenna is not matched, basically.
It's
Yes.
not match. Yeah. So you
Yeah.
have to have that match.
Yeah.
And then you have to have the size of the antenna
Yes.
comparable
Exactly.
to the wavelength.
Yeah. Okay.
Yeah.
So okay. Thank you. Okay.
Yeah. So when you go to such a high frequencies, then it will be
Well,
much smaller.
I'm not, let's say, right now, because let's say, I wouldn't say I quit. I just stopped my interest in telecommunication, let's say, time ago, when the telecommunication, let's say, the number of the information increased to such a level that. But what I remember, that the higher, let's say, link frequencies. Yes, this is around 30 gigahertz. Yes, and this is very, that in Poland there are, let's say, the few such links. In Great Britain, we have, let's say, like a dozen of such, because this is the very high frequency and very, let's say, the bit rate, yes, and the number of information which is sent using this link is very high. So, but let's say the internet and let's say the classical telecommunication, yes, and the voice communication use this radio link in this way, that the information is being sent by in using this frequency. Yes, this is but here we've got, let's say, like another chance to increase the frequency. Yes, to terahertz. This is I mean, is this let's say the kind of I would say the solution for the new telecommunication step ahead, or what do you think?
That has been one of the beauties or the interest of developing a Josephson junction as an oscillator is because it can go to that high frequency,
Okay.
depending upon the energy gap,
Yes.
and also it's tunable. So you change that voltage, you change the frequency. So there is a one-to-one correspondence. It's a voltage to frequency transducer.
Yes. Well,
So
basically, this is like I would say that kind of philosophical question, because yesterday we got like a let's say the talk about the number of information which we can send using let's say the classical telecommunication, and the question why we still introduce a new telecommunication standard. It's basically like a G5, G6, but because let's say right now, I mean, I'm using, let's say, I would say the 100 megahertz link connection, and as we see, this is still, let's say, like it's enough for the. So the question is, do we need such a very high frequency link? Maybe for some application, yes.
exactly,
But,
yeah, maybe for communication, yes,
but
maybe
this
this
is
is overkill.
Okay.
Yeah,
Okay,
maybe it's
thank you.
overkill for some purposes.
Okay.
When we started, I mean, as you rightly pointed out, physically, commercially, we do not have sources or antennas or anything that will be efficient at such a high frequency. When we stop at maybe 50 gigahertz, then maybe some military applications, they might go to 300 gigahertz.
Yes, right. Again. Okay.
So people that not common people will have access to that, because the militaries will want to have just a spectrum that they are the only ones in the world that can operate at this frequency.
Yes,
But
exactly.
but there are systems like the one that I'm showing you right now that they are tunable, and so you could have a wide range antenna if you're able to come up with an idea to to utilize it. But to get there are limitations, because the
Well,
systems sometimes are not well.
basically, I mean, this is interesting in a case of, let's say, let's say the science itself, yes, and the technique itself. I mean, even if we don't use it, let's say we have the possibility, yes, and we are, let's say, we have the force and the power to have this even if this like a not even needed for the let's say for the people, but it's nice to know that we are able to do such things. Yes.
Exactly.
Well,
Yeah.
we have been on the moon only once. Yes.
From the intellectual point of view, yes, it's very exciting, and I mean, for me as an experimentalist,
Okay.
it is exciting to see the correspondence. You do something, and then you have a certain theory that you believe it represents the system, and then you make a change, and then you can see that in an experiment. So that gives a very high level of satisfaction.
Okay.
And not only, it is also because it's difficult. Not many people will be able to put on a system in a single moment that everything will work so you can push a button on one side, see your results, make a change, and see a result that also corresponds to the theory that you're working on, and then come next week and then try to reproduce it. That requires a lot of effort.
Okay. So many thank you. I just for the answer.
Yeah.
Thank you very much.
Thanks, Alan. All right.
I mean,
So,
the first thing which we can see, actually, coming back to previous slide,
Yeah.
magnetoresistance. Can you, yeah. So magnetoresistance. So without ferromagnetic strip, the resistance increase much later with
Yeah.
temperature. So, but that's so you can so objectively, by looking on these pictures, you can on this resistant on the right top, you can you can confirm existence of magnetoresistance, but there is no much information coming on Josephson effect looking on those pictures.
Yeah.
Except well, so you see that that I mean, a resistance. So, okay, so definitely, but if you consider the classical situation, you have normal metal, and of the normal metal, you place ferromagnetic strip. This will be the case of nonlinear resistor, actually, and even modeling of some kind of magnetoresistance you can even observe in such type of system. So I'm saying that this is deeply so nevertheless, let's say let's say the last picture, so the right bottom, when current voltage characteristics, well, this is well, you proclaim to have very big the value of after factorization of critical current by resistance, but this can be due to many effects, like movement of vortices in your system, movement of spin polarized quasi-particles, so things like that.
Go ahead. Sorry.
So and then their existence of Josephson effects, I am not sure if you can say, just looking on the current slide, that you can say there is actually formally. I know that you do this later by Shapiro steps, but just looking on this picture, you are aware of existence of this magnetoresistance. You can hypothesize that there is certain nonlinearity in current voltage, but it's assigned to both cases, and also you can have this existence of Josephson effects due to the fact this is high temperature superconductor. So I'm saying that at least those slides given here are not really informative, or doesn't represent the criteria for let's say for stating about Josephson effects induced by ferromagnetic strip, at least not yet. That's my kind of personal belief. Maybe not belief. That's just logical kind of consequence of logical view in my as I assume, right?
Exactly. So I mean, the only thing I'm claiming here, Chris, is that I make two different bridges. One that has an iron dot deposit across the bridge, and the other one doesn't have one. So there are some changes. So the one this black one that has no magnetic dot.
But just without ferromagnet. But was there any metal? No. One was without. One was just a rectangular superconductor, and on another one was a rectangular superconductor with plate strip on the top.
Yes, exactly.
So those pictures, let's say, doesn't really imply yet about existence of special form of Josephson effect in the structure under your observation.
Exactly. Yeah, it just shows that there is a difference. It's
a difference is kind of obvious, maybe not obvious, but you do expect certain level of difference, let's say.
Yeah. For many things, we are placing a metal in contact with a superconductor, so we are kind of affecting the superconducting state. The systems, the level of copper pairs. But there are this type of system. There are so many things going on in there, Chris, that I cannot tell you. Okay, I can explain this fully with the formation of a Josephson junction. This is not a classical Josephson junction effect. This is an effect where one system is affecting another, but it so happened that the system that is being affected is a continuous film of superconducting material, and then somehow I make a disruption in between. So it's like on one side I have fully superconducting, and the other side I have similar fully superconducting. In between, I have something that I don't know what it is. So many things is happening. And so this will show you in the next slide.
Let us say, if too many things is going to happen, if too many parallel physical processes are going to happen, you need to first purify the system because you are not able to conclude anything if too many processes are taking place at the same time.
Yeah.
So you have to purify, at least turn off certain or reduce certain physical mechanisms. So they're just, I mean, by changing the sample or like in there is lack of. So let's say you place ferromagnetic strip directly on the top of superconductor. So from theoretical point of view, it's a nightmare. From equations point of view, there is a Kuboki work on that. Also my work on that. So this is absolutely theoretical nightmare. So you need to purify, and one way of purification is you have superconducting bridge as you stated.
Yep.
Which actually, yeah, I would say this bridge, this is already built in a weak link somehow, right?
Exactly.
And then on the top, you place insulative material and then you put a ferromagnet.
Exactly.
So then you can purify. Then you can purify.
Yeah.
Otherwise, you cannot, right?
Yeah, exactly. So, but I'm just showing you the first approach. You know, we have a basic idea. Let's see how it works. So at Maeda's lab, we have the ability to create the films. Then we went into the next step. Can we pattern the films? And then the next step is, once we are patterning the films, let's add some different materials. So this is basically the geometry. We have a superconducting film of a fixed thickness. This is DS. Then we can place another material top, a strip, a dot of also different thickness. That will be the DM. The M will be for magnetic, the S for superconducting. So, you know, the growth on this direction will be the thickness. And then we have a width of the bridge, so that it will be WS. And then there will be a width of the magnetic strip, so that would be WM. So we will play with all those different values of geometrical. So in here I'm showing you one of the samples that we made. So here on the top and on the bottom, this is the substrate, is lanthanum strontium aluminum oxide. This is basically sapphire. And then on top, we create the lanthanum strontium copper oxide. This is the superconductor. So this is patterned into a bridge. In this case, the width is 2 micrometers. So the WS, so the width of the superconductor is 2 micrometers. The thickness of the film is 600 nanometers. Now on the magnetic part, on the strip that is in this case is iron, and it has a width of 400 nanometers, and the thickness of the iron is just 600 nanometers. So this is one of the systems that was measured, and then that would be a representation from the side. So the substrate under the continuous film of LSCO on top, and then on top of that the iron. And then what we think is that somehow the region that is right directly underneath the iron is changed. So we have a fully superconducting wave function on this side, the same on the other side, and then somehow it's modified in between under the iron, and then there is some kind of a tunneling that pass the information from one side to the other. So as Chris mentioned, this is a complete nightmare. There's so many things going on in here, so many things that I discovered after I made the samples that make myself impossible to really pinpoint what was going on. let me list some of those things for you. Iron oxidizes, so it has an enthalpy of formation. You know, the iron will make iron oxide, and it would take some energy to extract to be oxidized. So in between the interface, some of the oxygen is being removed from the superconductor. So that makes something, you know, some problems. What else I'd like to point out to you? So the iron is a magnetic material. So what about if there is a way or a possibility or a mechanism that some of the electrons that are magnetized in a particular direction, and we can magnetize this by an external magnetic field, how about they will leak into this region? So we would destruct the superconductivity in that way as well. So we have two things that are very difficult to separate one from the other. So what Chris was suggesting of adding an insulating material, that might help with the problem. Okay, questions to this point before I go to the next slide?
No, it's understandable.
Okay, thanks. All right.
Okay. Two superconductor and let's say the isolator in green. Yes. Yes. This is isolator.
Yeah, exactly. So this green here, it is what Adam. What I want to point out is this is an easy way to create some kind of a separation between this region and that region.
Yeah.
I mean, it's completely different to anything that I showed you or had been working in the past. So if I go back to you know the models, the different approaches to make just some junctions, there is nothing here that will be similar to what I showed you just a minute ago, except for this one. I mean, this is the only one that is kind of similar. We've got a continuous film, and somehow we use an electron beam ray to knock off some of the electrons. So that's what this Topalgo and this group of people, how they describe the physics. You know, they create a film, a kind of a bridge, and they put across a high energy beam of electrons. The electrons come and they knock off some of the oxygen, and that's how they create the junction. And so this is absolutely different to any of this over here.
Okay, thank you. I'm just just curiosity. Okay.
No, thanks so much for the question. So and then this is what we think have here. You know, this is a continuous film. We only simply place the dot on top, and then somehow modify whatever is under. So there's no type of interface. It's just one on top of the other. And that's very easy to make. So we create the best film that we can create, and then place something on top. Of course, maybe to really find out what's going on, we should put an insulating first and then put the other one. And I think this is the basis for what Professor Pomorsky is doing on his theories. Am I right, Chris? Some of the stuff. Are you there? Maybe you left.
Yes, I am there. Sure, I am there. You know, yes, I'm actually for a couple of hours already because I have already before some meetings. But anyway, the thing is that theory for that system is very nasty. It's theory nasty. Of which led me to hit nasty from complexity point of view, because that's a set of nonlinear partial differential equations that are coupled. So it's a nightmare from algorithm point of view. And because of that, I have developed a relaxation method. And this relaxation method is quite stable and provides approximate solutions. Nevertheless, this method is not ideal. But of course, there's a possibility of, I mean, well, you need, basically, there's such a way of saying, even in theory, that in order to find something, you need to expect something. And it's very hard to expect something specific in such a system that is so much complex.
Exactly.
So
Many things are going on.
so that's a one thing. I mean, there are tons of things that are not fully resolved. Even the quality of this interface of ferromagnets. So like, do you have diffusion of spin polarized quasi-particles from ferromagnetic
Exactly.
strip into superconductor? You have diffusion of Cooper pairs from superconductor to ferromagnet. You have you have the whole dynamics of I mean. Yeah, you have like condo effect and things like that. There's tons of things that goes here, and this is even to make it even harder. There is built-in layers, because you never mentioned that in your talk today, that in high TC superconductors you have very high level of anisotropy, and this in anisotropy you have C axis and AB plane. So
Exactly.
you have built-in network of Josephson junctions. So I mean, okay. So definitely you can try to attempt RCSG model. You can, but basically it's more than necessary to it. I would say I would rather insist on study of low temperature superconductors in such kind of geometry,
Yeah.
because it allows you to reduce the complexity, and it allows you to have some level of understanding. And as you know, nobody fully understands high TC superconductors. Okay, maybe people do understand to a certain degree, but rather uniform systems, I would say. I don't know, but that's so. I mean, I would say that the problem can be even not fully solvable from practical point of view. So that's just, yeah. I mean, first thing is sometimes to reduce complexity. That's more than necessary. Okay, that's my
Yeah.
comment.
No, I will agree that we could try to go to low temperatures, and then use.
No, low temperatures will not. I mean, lower complexity of samples. So you are using like LSCO material that is already very complex by itself. But I mean, I'm saying usage of BCS superconductors in such type of
Exactly.
geometry makes sense,
Yeah.
at least as preliminary research step.
Exactly. So let's say we move from high TC, we go to low TC, aluminum. Okay. So, and then we try to see would aluminum be affected by an iron dot? I mean, and then we can say, yeah, there could be a way to some of these magnetically polarized quasi-particles leak into the aluminum, and they would change the wave function, and then you can create the junction that way. So yeah, I think this is a very possible system. And if you do a Google search, I don't think these have ever been attempted. I
Well,
guarantee
if
you that.
if people doesn't has full controllability on the system, usually they don't publish the data because they're not certain of. I mean, this similar types of systems for sure has been mastered to a certain degree. There is one work in this direction, theoretical work, which actually has a remarkable low number of citations as when we consider that the one of famous physicists did it. Yeah, so my physical statistical DB paper is cited by this work. There is one work
So you have cited a work like that. Yeah, let's
yeah,
maybe talk about later.
yeah,
See what
sure,
because
sure.
uh, I already have submitted a couple of grants applications for this type of work, and every time you do a grant application, you have to see what had been published, and it's actually, Chris, until this time, I don't remember any system. You can pick, let's say, aluminum or niobium or MgV2, which is another kind of metal, maybe interesting type of system. and take away all the ceramics, because the ceramic has the problem that they will lose the oxygen, and that's another complication, and they're maybe not fully BCS and more difficult to model. But if you go to the very classical materials, very little have been published on that. So we can talk about this later. But this is something that I wanted to suggest to you to go to from the point of view of theory and also from the point of view of experiment. If we can find some kind of a collaboration to do that, we discussed of how simple the system should be, and we make it, either with all the capabilities that I have, in a way that you can model that, and then you make it. One of the students will make a thesis out of that.
We will see. We will see. Okay, please continue with your presentation.
Exactly. So so this approach was very rapidly marketed, patented by Professor Maeda and myself. So we had a patent, a Japanese patent in 2007. Then in 2012, we got this US patent. And a patent doesn't mean anything. It's just a lot of money that somebody pays for getting a piece of paper. Unless you make a device, you have to apply this principle to make a device that you can sell it, and you only have 20 years to do marketing on that. So once 2032 comes around and we have not made any devices with this, everything, all the effort will be lost. So already 10 years have passed and still no results. There are so many things that have to be in place at the same time. You have to have the expertise to go to the right dimensions. You have to, have a very clean interface of whatever you want to make it. So all of those factors, sometimes they take a lot of effort, a lot of money to put together at the same time. And so most of us, I'm a physicist. I don't have access to industry. I haven't convinced anybody to say, okay, let's invest in this technology. And I will tell you about this, Chris. I mentioned to you this person in Norway, in Oslo, Per Lien. He's one of my contacts in LinkedIn. I sent you the contact through our conversation earlier today. So, these type of people are interested in using these systems as some type of a SFQ electronics that will allow them to do some Bitcoin mining. So, if we can make some type of a circuit that will dissipate less energy and operate at a much higher frequency, then, mining might be possible in a shorter amount of time and with less consumption. So, there's some people there that say, okay, why haven't we developed superconducting electronics yet? What is the problem? So can you think about what the problem is?
For once, the high developmental costs putting the barrier. At this point, for most of the corporation, it's just cheaper to simply invest in better conventional electronic systems than to shell out money for the superconducting electronics, unless they are promised a big payout.
Yes.
Though I would be skeptical about using Bitcoin as potential source of big payout right now with the situation at stock exchanges right now. Bitcoin exchanges. Sorry, stock exchanges was the misnomer. Maybe the closing of several Bitcoin exchanges isn't too optimistic scenario for using Bitcoin as promised big payout, for at least in my opinion.
Exactly. So some people are willing to make themselves rich, invest a little bit of money to do some basic research,
No, this is always a consequence of short path that somebody wants to become rich too quickly, or he wants to become too wise too quickly. Then usually he doesn't becomes too wise, but he pretends that he becomes too wise. Or and the same is with richness. So GP Morgan, there are certain traditional banks that never believe in bitcoins and things like that, but some people still do. But now we have we have experience already, you know, various things. Just watch history. What is? I mean, talking about superconductors applied on big scale. Of course, only rapid single quantum flux electronics is the current candidate for
Exactly.
that. And but there is lack of random access memory for that. So that's the reason why it was not deployed on a large scale. That's one of the reason. And second of the reason is obviously it only works for big data centers. So I think there's issue of flexibility. I mean, simply saying semiconductors are so practical and so scalable and so common. And I mean, there must be a new cold war in space to promote superconductors. So in order to promote superconductors, you need a factor that induce Cold War, and then
Exactly.
and then people will do it. All right.
Well, I would say that the Cold War right now has to do with, maybe global warming could be, or this particular catastrophe that kind of unifies the whole world, that kind of drive us into saving more energy and doing things a little bit more efficient. So that might say, somebody would say, okay, superconductivity is our only way to maintain our high level of energy consumption without losing so much energy. So maybe that would be the driving factor. And I see this in the U.S., Chris. The whole country is trying to get to increase how people use electricity. So somebody says, yeah, why don't we create the new generation of high temperature cables to connect all this. So I mean, this is one way. So at least some money is being used to give to private companies to develop new technology based on superconductors. So I know this happened from the 87 to early 2000s. Then there has been a whole 10 years, 15 years of nothing. But then right now it's picking up again. And I'm not sure if you see the same thing I see.
Well, I would tell you in a very critical way that every fashion is cyclic.
Yeah.
So you know what I mean. People start to wear clothes that were fashionable in 60s or 70s, something like that. So even of course the balanced development and the low energy consumption is a phrase that might support this research, right? For sure.
Exactly. Yeah, for sure. Yeah, so that's what I put in my eggs into that basket. The ability to convince people that we need to give a second chance to superconductivity in general, and it's happening. We got the quantum computer people. The most of the circuits are superconducting based circuits. They're not what I described here, but it's superconductivity. So at least some interest is being driven into that region again. And it's been 100 years since it was discovered, and only in the 60s we got this phenomenon. So it has not been too long. All right, let's continue. Sorry guys, I'm getting a little bit tired. So the next step will be to just characterize these samples. So again, this is the same resistance versus the temperature curves. We do an IV, but now we vary the temperature everywhere. So we start for the lowest temperature, 5 kelvins. It doesn't show on this scale. So this is 14 kelvins. 5 kelvins will be somewhere around here. So from 5 kelvins to 19 kelvins, which is around here. So we stop at every value in temperature, and then we do an IV, which is basically, we repeat this curve. So this curve at 50 kelvins, 15 kelvins is this one in yellow with the triangle. So this curve would be a blow up of this curve over here. So you can see the yellow one goes from 0 to about 30. So it's the 20. It is the 20 microamps. So you can see here, this is in microamps. So the yellow, it's around there, around the 20. So I had to show you, but then these curves shows a series of curves like this only for the for the first quadrant of current voltage. Sorry, voltage current. All right, so from 5, 7. I mean, I have all the temperatures, but I only plotting few of the points there, so you can see how the IV is developed. And then what I do, I calculate the critical current as some kind of a cutoff value in voltage, and I measure that and I plot it versus the temperature. So here are the VIs for every temperature. Then out of this curve, I get the critical current, and then I plot that as a function of temperature. So this is the kind of plot that I get. And then all the measurements are many measurements taken in between, and I only show you here the value. So this one is the orange, or this kind of reddish color is 13 kelvins. This is 15 kelvins. I'm not sure if you can see it from the plot. So this is how it will look. Then this is the result for using iron. But then we went further. Let's see, something stopped here. Okay, we went further, and we created a bridge with iron, which is the one, the red curve. So this is basically, and also we normalize the values with the critical temperature. So there are 3 different systems, so they have different critical temperatures. So, but the black curve represents the bridge that has the iron. The other one has copper, which is a non-magnetic value, but it has a different curve. And then the last one, the green one, is just a bridge, the plain bridge with nothing in it. So and this is just a curve that represents this value, the 1 minus 1 T over TC. So I plot the data. I chose to plot the data in this fashion to compare this to a classical results. This was published in this review paper by Delling and Kleinsner. This is for high temperature superconducting Josephson junctions, and so basically you can see that the bridge that has the iron behaves like one another Josephson junction made with high temperature superconductors, and it has this this curve shape, and the others do not have that. So that's another indication that maybe what we made it can be comparable to other types of high temperature Josephson junction systems. So yeah, questions on this curve. So I just try to simulate what we obtained to what other people had obtained. So our results tell us that we are creating a type of superconducting, non-superconducting system.
But still, this is in the framework of our high TC superconductors. This left
Exactly.
plot, right?
This one on the right is high TC as well.
So it is, yes, it is a bit comparable, nevertheless not fully. But Okay, I got the point, because there could be very much dynamics of various exotic vortex configurations and things like that. That's pancake vortexes, abricosal vortices, Josephson vortices, and many other stuff. Okay.
Exactly.
Okay.
So yeah, I mean, this is not a fully comparison or a full proof of the system, but you know, we made experiments on two different systems, one with nothing, and the curves is completely different, and one with you know, another metal, but it's not a magnetic metal. So it creates some changes, but you know, what is this? Is, you know, it's not the same as the other one.
Yeah. Okay. Go ahead.
All right. Okay, and then the last proof was, you know, we see how the critical current changed at a fixed temperature. In this case, was 18 kelvins. So we place ourselves as 18 kelvins, which, you know, the characteristics looks like, you know, like this. Well, it's not shown here between the 17 and 18, so it's somewhere around here will be the curve, and then, you know, we apply an external magnetic field, and then if we kind of calculate the area that is being made by you know, the width and the width of the magnetic strip and the width of the sample, you create some kind of an area that is normal, and so through that region is where the magnetic field will get into the sample, so it gives you some area, and then you can see like how the critical current modulates, and so we'll do the calculation, and it kind of the width of the magnetic strip multiplied by the width of the superconducting bridge give us an area, and it's kind of in between. This will be the flux quantum for in these particular units for the classical flux quantum, and then this will give us the applied magnetic field, and then we'll see that by using those values that we obtain directly from the curve, there is a correspondence between the area that we obtain and that is physically made and what we measure. Let's see.
Well, that's a very important thing. Okay, so you have magnetic field versus critical current, right?
Versus critical current, and we know that it will modulate. So the magnetic field change the critical current.
Yeah, that's for sure. But the thing is that magnetic field. So definitely you have built-in magnetization in ferromagnetic strip. That's what can be seen from that plot. That's a first thing. Second thing, you have certain events that are not fully resolved as those two separated dots. Well, does indicate some kind of switching, like some kind of vortex occurrence or vortex induction. It's hard to foretell.
It's hard to tell.
But most likely the plot given here does show that this is not typical sine phi relation is not typical. This is most likely Varphy type of Josephson junction. So I'm saying that the ground state of this Josephson junction doesn't need to correspond to zero current flowing via it. So by some chance, actually, I have one publication stating a similar system to be like that. Okay. But this plots clearly show that you have P Josephson junctions, and you can have also arbitrary shifted by arbitrary phase. So that's a candidate. But as I already mentioned to you, it's absolute nightmare to resolve all this mechanism. It's simply too high level of complexity.
Yeah,
that's supposed to be reduced. That's what I can say. Okay.
No. If I have a chance to do a redo of all these experiments that I did in my doesn't say, because I'm not sure if you remember, Chris.
I know what you say. No. That's not the point. The point is that attacking high TC superconductor from very beginning. I mean, you get the data, but no theoretician in the world will dare to analyze this data because the system has too many unbiased or not fully controlled elements.
Yeah.
So it's absolutely necessary to go into BCS superconductor and to be much more humble as about level of complexity. Otherwise, you die out. You have results that you cannot parameterize by theory. So that's in a way half of results, something like that. Anyway.
Yeah. No, I agree.
Go ahead.
But I wanted to comment something like for the future. Like if we can think about the future, and then let's say we will talk about how can this be repeated, or what system can be used, or how everything has to be changed. Having the magnetic dot there is so, I think, technologically, from the technological point of view, is so important. You know, we can have, if you believe there are vortices in the system,
I don't need to believe. For sure there are. I mean,
but it depends, Chris. Depends if you have a type 1 or a type 2 superconductor.
But you have built-in vortices in materials. So Josephson vortices for sure occur. That's
exactly. Yes. If you make a squid, you have a Josephson.
They even occur naturally without any modifications of a bulk. So that's how it is.
Yeah, we can talk about that.
All right.
My understanding of a Josephson vortex is that you have you have to get a squid type of geometry to have the vortex, the Josephson vortex.
Okay, we can.
The abricos of vortex is, you know, there will be in type 2 superconductors, and most films are type 2, no matter what material you get. But then you have the magnetic dot. So the magnetic dot will kind of you know, focus those vortices, abricos of vortices, into the system itself. So yeah, I mean, there's a lot of work to still to be done on this.
All right. Okay. Just continue, Luis. All right.
Okay. So, and then we add some AC signal. So again, you know, we'll take the current voltage. In this case, it's only at 2 gigahertz with, you know, certain attenuation, and then we see again those. This is the characteristic resistance when you plot this versus the voltage on this VI. We see the same curve that I showed you earlier today. So, you know, some dips that correspond to the existence of some Shapiro steps. So all of this, Chris, occurs on that system that I showed you. So a type of a Josephson phenomena, not fully clean, understood, kind of dirty, but, you know, everything seems to be there for the future, I believe. And then, you know, I'll if I do the calculation, the first step, which is this one over here, it will occur at about 4 microvolts, which is where I showed them very clear. So this will be the first step. There's something called the half step, but I won't go into that one. But there is a first step here at 4 microvolts. So the second step will be at 8, and so on. So they seem to all to be there and to occur where you expect from the theory to occur. Okay, and so that, I think these measurements that makes it a little bit more complicated. Now, all the measurements that I showed you before is for 1 junction. Now, how about if we put 2? So that's what we did here. We have 2 bridges, 2 junctions, I mean 2 magnetic dots, and then you do the measurement. So everything is repeated again, and then you see again some oscillations. You know, this is much more complicated, but again, it's all done on these systems which are almost impossible to be modeled. And then, you know, we'll see something interesting. What it is was still not clear, but we did a lot of work. By the way, all of this, Chris, was done by Kitamura. And Kitamura did that after I left. I'm not sure if you were still there when he was there.
I don't remember, but somehow I do remember. Yes, Kitamura's.
Yeah. So, I left the lab earlier, but I made many samples. I left them at the care of Kitamura. He worked really well. We work at the distance. So he did all these measurements on his own. All
Yeah.
these measurements were done by Kitamura, and then he compared that this set of measurements with something that Rogala did on his systems. So we were getting similar results. He even got this curve. This is also from Rogala's paper. So this is what he got, and this is what Kitamura got. So in my way, in my point of view, he did a lot of work, but I don't think Maeda likes him. So at the end, I don't know if he ever passed the master thesis.
No, I think he passed. I don't know. I don't know.
Ja przepraszam, jest trochę późno, bo mamy tak przesunięty czas po prostu. No, zadzwoń, jak będziesz miał potrzebę jutro, ewentualnie rano, bo ja dzisiaj miałem taki dzień, że musiałem się
I'm sorry for I have to turn off the Adam. All right, so Luis, go ahead.
Okay, so this kind of completed the job, the working at Maeda's lab. Chris, is getting pretty late.
No, just finish. Just go to conclusion. Just finish. Good.
I'm not going to. The next step is all the other work. It's completely different.
Like what? Okay, just give very briefly. Just let's say.
Yeah. So this was the work in Zurich. So I joined in. This is Andreas Schilling. This is the guy who obtained the highest known high temperature superconductor temperature with mercury-based superconductor. And then he has these two, a postdoc or assistant, Andreas Engel, and then Holger Bartov, and he was the graduate student. So basically what they did, we use a much higher, much more precise, better clean room at ETH, and basically a system to create a very narrow photon detectors. So this was published by then. Is we used niobium nitrile, which is a very interesting superconductors, and so Holger worked really hard to get these islands very narrow. So this is about 15 nanometers. And then this just lasted for a year actually, and then I went on to be like an assistant visitor professor there, and I work on a similar system, but again I repeated. In this case, it's niobium nitrile, and I use nickel.
Yeah, so that's really cool experiment. Okay, and
yeah, so, then I got similar results. I'm not going to go into the details of here, but I saw, because of this system, the niobium nitrile was so thin and it's so resistive that many times I put the nickel on top, and I could have absolutely complete destruction on the superconductivity. So that was, that required to do a more extensive study. The capabilities were there, but there was not the funding. So, and the funds ran out, at least for my side. And then that's where everything stopped, But so I got to the point where I repeated the ideas. I think I went to Poznan with you to show these results, but then after that, there were no more funds to continue. And then new materials needed to be studied. For example, changes into aluminium, and then other metals could be used as well.
No. Don't go for too many. This is already. I think this is this result is quite publishable, and also, well, at least there's no nightmare with complexity. At least, no. There is some level of complexity, but it's reasonable complexity.
Yes.
So, well, okay, still, this is for a magnetic material on the top of NBN, right? And I
exactly.
is for, all right. Do you have
Yeah.
without ferromagnetic material on this instead of Ni?
Well, I have to look. I believe I made the samples with copper. and
But
they
do you
were
have
completely
IV
different.
or resistance?
Yeah, yeah. You
That-
know,
that-
I'll have,
that's more than crucial to have it.
yeah, yeah. No, that's the thing, Chris. I was going almost towards the end of my tenure at ETH, and there was no, it was not complete. I was very much focused on one thing. It was to get the oscillation at a high frequency. That was my focus. So I left many of the research. There are many gaps. You know, we have the capability to do it, and I was basically doing this thing. So if we have funds and we have a student, you know, this is something that you can teach fabrication to one student and then tell them, okay, try, you know, do this, spend 3 years or how many years on whichever level of thesis doing something that is quite doable, and you know, it's at the level of any graduate student, for example. And then a nicer research can be completed and presented.
All
So
right.
guys, that is the end. This is the last slide, and this is basically what I had shown you. You know, there are many systems that present remarkable superconducting properties that can be put into devices, and then something I didn't focus was that the measurement technique is quite crucial, and so I used something called the DC delta pulse. I didn't talk into that during the talk, maybe slightly, just to give you that, but it's also very different to what many people do. Okay, that's the end, Chris.
All right. So thank you for your talk. So guys, do you have any questions?